वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे. रयते मधुनी नव्या युगाचा माणूस आता झरतो आहे. वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे. रयते मधुनी नव्या युगाचा. कर्मवीरांचे ज्ञानपीठ हे शक्तिपीठ ठरते आहे. शाहू फुल्यांचे समानतेचे तत्वज्ञान.
काय प्रॉब्लेम माहिती का तू?
नेट लागेल ना त्याच्यासाठी, म्हणून ते कनेक्ट होईना.
काय करायचं, कशात कनेक्ट करायचं?
झूमला
कोण
मीटिंग
कोणासोबत?
कोणी हो? आम्ही दोघं करत राहतो एक एक छोटी छोटी वेबिनार आपली.
धर्म जातीच्या पादगांधींचे मूल्यमान मी जपतो आहे. रयते मधुनी नव्या युगाचा माणूस आता झरतो आहे. वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे. रयते मधुनी नव्या युगाचा.
त्या शिकते त्याला हेडफोन देतो.
गरिबासाठी लेणी मोडून लक्ष्मी वहिनी झाली आई. कमवा आणि शिका मंत्र हा करुणाईला प्रेरक होई. स्वावलंबी वृत्ती ठेवून दीनदलितांसाठी अण्णा तुमची झिजली चंदन काया अनाथ जीवा सदा लाभली मातृदयी तुमची माया मधल्या नवसृष्टीचा निर्मिक तोही ठरतो आहे रयते मधुनी नव्या युगाचा माणूस आता घडतो आहे वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे रयते मधुनी नव्या युगाचा
हॅलो हॅलो
जीवनातला नील जावा प्रबोधनाची पहाट व्हावी इथे लाभले पंखले मुनी उंच भरारी नभात घावी प्रतिभाशाली बहुजनांचा वेलू गगनी चढतो आहे रयते मधुनी नव्या युगाचा माणूस आता घडतो आहे वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे रयते मधुनी नव्या युगाचा अनभा
वीडियो ऑफ है म्यूट है
निको, तुला कानात ऐकायचं आहे का? हा.
मला बोलतो
Not audible. So please audible.
Hello, sir. What is the timing for starting?
I have. A very fine and pleasant morning to all of you. A warm welcome to the esteemed resource persons, attendees, and participants, my fellow colleagues, for this webinar on advanced materials and their applications, jointly organized by the Department of Physics and ICSE,
Sound is not clear.
that is Chhatrapati Shahu College, Kolhapur. I am Dr. Sabiha Faraz from the Department of English. Please join me welcoming our principal, Dr. S.T. Sarunke, sir. Guidance. This webinar has been organized. Present for this webinar are Dr. V.V. Killedar, convener of the webinar, Dr. R.S. Dubal, sir, our vice principal,
Dr. S.M. Sathe, IQAC Coordinator. Before we start the deliberations, I request your Rayat Geet, which enshrines our Sanstha's mission and vision. Let's commence this academic activity by playing the Rayat Geet.
रेड चालू करा क्या
नव्या युगाचा माणूस आता घडतो आहे वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे रयते मधुनी नव्या युगाचा माणूस आता घडतो आहे वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे रयते
माईक इथेच का बाजूला काय
कर्मवीरांचे ज्ञानपीठ हे शक्तिपीठ ही ठरते आहे शाहू फुल्यांचे समानतेचे तत्व मानसी मूर्ते आहे धर्म जातीच्या पादगांधीचे मूल्य मानवी जपतो आहे रयते मधुनी नव्या युगाचा माणूस आता घडतो आहे वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे रयते मधुनी नव्या युगाचा गरिबासाठी लेणी मोडून लक्ष्मी वहिनी झाली आई कमवा आणि शिका मंत्र हा करुणाईला प्रेरक होई स्वावलंबी वृत्ती ठेवून ज्ञान साधना करतो आहे रयते मधुनी नव्या युगाचा माणूस आता घडतो आहे वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे रयते मधुनी नव्या युगाचा दलितांसाठी गणना तुमची झिजली चंदन काया अनाथ जीवा सदा लाभली मातृहृदयी तुमची माया शून्यामधल्या नवसृष्टीचा निर्मिक तोही ठरतो आहे रयते मधुनी नव्या युगाचा माणूस आता घडतो आहे वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे रयते मधुनी नव्या युगाचा गाठले मुनी उंच भरारी नभात घावी प्रतिभाशाली बहुजनांचा वेलू गगनी चढतो आहे
हॅलो
रयती मधुनी नव्या मुलाचा माणूस आता झळतो आहे वटवृक्षाच्या विशालतेचा मोहन भाला
हॅलो
तो आहे रयते मधुनी नव्या मुलाचा.
May I request our principal sir to take over and welcome the attendees and resource persons.
Good morning.
Good morning.
On this occasion of webinar organized by Department of Physics, Rajarshi Shahu College, Kolhapur, on the behalf of this college, I welcome today's dignitaries, Dr. P.S. Patil from Shivaji University, Kolhapur, Dr. Ubale, Joint Director, Higher Education, Kolhapur Region, Dr. Sartale, Dr. Shirke, Dr. Devan, and all participants, also all organizing committee of this webinar. Rayat Shikshan Sanstha is the parent institute of our Rajarshi Chhatrapati Shahu College, Kolhapur. It Sanstha was established in 1919 as one of the leading institute in Asia. The Sanstha is celebrating centenary year in 2019. The value of its contribution to education in general is enormously great, as it has from the very beginning tried all its best to lay emphasis on the education of the downtrodden, the poor, and the deprived classes of the society. The founder of institution, late Dr. Karmavir Bhaurav Patil, was a man of masses who devoted all his mind and heart to the cause of their education. The institute's motto is education through self-help, which speaks for its emphasis upon the dignity of labor and its social orientation. During last 90 years, our parent institute, Rayat Shikshan Sanstha, has proliferated to such an extent that today it runs 41 senior colleges, 2 B.Ed college, just 1 engineering college, law college, and Sanstha is having 432 high schools, that is secondary schools, and 25 primary schools. There are more than 5 lakhs students learning in these different institutes. Our Sanstha is having 14 colleges accredited with A grade by NAC. 6 colleges of Sanstha has autonomous status. For the outstanding work for the upliftment of the deprived unprivileged class, the Sanstha has been honored with the following prestigious awards. Dr. Babasaheb Ambedkar Award was awarded by Government of India, and in state level, Government of Maharashtra has awarded Dalit Mitra Puraskar and Adarsh Shikshan Sanstha Puraskar to this institute. Also, there are different awards: Rajarshi Chhatrapati Shahu Puraskar, Sant Gadge Baba Seva Puraskar, and Dr. Punjab Rao Deshmukh Smriti Puraskar. About this college, I will say the Rajarshi Chhatrapati Shahu College, Kolhapur, was established in year 1962. The college was named as Rajarshi Chhatrapati Shahu College from Kolhapur in the memory of Rajarshi Shahu Maharaj of Kolhapur, a great social reformer of Maharashtra. The college has celebrated its Golden Jubilee year in 2011-12. Recently, the college has been reaccredited with A grade with CGPA 3.07 in the third cycle by NAC. College is awarded with Karmavir Paritoshik in year 2015 by Parent Institute. Our college is a reputed college providing quality education in the field of arts, commerce, science, and computer science. It has tradition in sports, mainly in wrestling and kabaddi. Mr. Sambhaji Patil, Director of Physical Education, was honored with Shiv Chhatrapati Puraskar, awarded by Government of Maharashtra, and Kolhapur Bhushan Puraskar, Krida Sanganak Puraskar, Dadoji Kondev Puraskar, and Motilal Joshi Foundation Puraskar. Recently, Dr. Ramesh Bendigiri is honored with international status as the chief coach for Thailand girls kabaddi team and working as a coach for pro kabaddi competitions. College has glorious tradition of wrestling and kabaddi. Majority of faculty is engaged in research and have completed number of minor and major research projects sponsored by government organizations and non-government organizations. The college bears well-equipped laboratories, swimming tank, and big playground of Olympic standard. The Department of Physics was established in 1992. It was inaugurated by Professor Dr. Michael Spallart, CNRI Lab, France. Department is rich in terms of resources and infrastructure, has enough latest audio-visual equipment and online study material. The department organizes extracurricular activities such as conferences, seminar, group discussion, project, parent-teacher meets, and number of student-centered activities. Dr. Killedar, head of the department, is honored with Best Teacher Award by the Vatsalya Foundation, Kolhapur. With this brief introduction of Rayat Sanstha, my college and physics department, once again I welcome all of you for this seminar, for this webinar organized by Department of Physics and IQAC cell of this college. Thank you. Jai Karma.
We are really privileged and honored to have with us today the chief guest, Professor Dr. P.S. Patil, Dean, Faculty of Science and Technology, Shivaji University, Kolhapur. I request the convener of the webinar to introduce today's chief guest.
Thank you. Think of a devil and devil is there.
कोण आले का हा बरोबर Hello. 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 I am Dr. V. Killedar. Come, the chief guest, Professor P.S. Patil, Professor Dr. A.U. Wale, President of today's function, Dr. S.T. Salunge, resource persons, Dr. S.D. Sartale, Dr. P.M. Chirge, Dr. R.S. Diwan, organizing committee members, patrons and participants from all corners of India for their overwhelming response to this national online seminar on applied materials and their applications. It is my pleasure to read highlights of very rich biodata of Dr. P.S. Patil. Professor P.S. Patil completed his MSc and PhD from Shivaji University, Kolhapur. He is working as a professor and HOD in Department of Physics, Shivaji University, Kolhapur. He is also working as coordinator, School of Nanoscience and Technology. He is also working as a dean Faculty of Engineering, Shivaji University, Kolhapur, BOH Chairman of Physics in Shivaji University, Kolhapur. He is one of the top 10 knowledge professors in India by Careers 360 ranking. He received Outstanding Research Faculty Award by Careers 360 ranking in India. He has produced 45 PhDs and 6 MPhil students. 5 PhD students are currently working under his guidance. And I hope that within next 2 years, he will complete half century of PhD students. He has published more than 460 research papers in the international and national journals of well repute, and abstracts greater than 550 in national and international conferences. Total citations for the papers is 18,114. H index is 68. I-10 index is 391. Research get reads 1,07,000. Total research papers viewed by Medley is 4,51,000. He has written 4 books, 5 book chapters, and 1 Korean and 3 Indian patents. He is a recipient of prestigious German Academic Action Service Fellowship Award from Meitner Institute, Berlin, Germany. He is a recipient of prestigious Brainpool Fellowship Award by South Korea. He is also a recipient of prestigious Brainpool Fellowship Award by South Korea, Chonnam National University, Korea. Best Microscopy Image in the World Award from Nano Today Elsewhere publication. Best Cover Image Award from Materials Today with the impact factor 21.79. He has received Best Teacher Award from Shivaji University, Kolhapur. One of his PhD students received Best PhD thesis in the world. He is working as a referee for many international journals, including American Chemical Society. His research work on electrochemical smart windows ranked 6th in the world and 1st in India. ZNO-based toxic gas sensors ranks 20th in world and 1st in India. CZTS solar cells ranks 11th in world and 3rd in India. He is working as editor, review editor for international journals, working as international research project reviewer of Pazzi Foundation, Israel. He is also working as international PhD reviewer, Cairo University, Egypt. He is visiting professor, Chonnam National University, South Korea. He has completed individual projects worth of rupees 4.75 crores. With this brief biodata of Dr. P.S. Patil, I request Dr. P.S. Patil to give his chief guest address. Thank you.
Now I request Dr. P.S. Patil to deliver his address.
Dean, Faculty of Science and Technology, Shivaji University, Kolhapur, Head, Department of Physics, and Director, School of Nanoscience and Technology, Shivaji University, Kolhapur. I'm indeed very happy to be a part of this conference, which has been organized by Rayat Shikshan Samsthas, Rajarshi Chhatrapati Shahu College, Kolhapur. The national conference entitled, it is an online seminar on advanced materials and their applications, which is organized by Department of Physics and IQAC Cells, Chhatrapati Shahu College, Kolhapur. On this occasion, we have the president of this inaugural function, Honorable Principal Dr. S.T. Salunke sir, Honorable Dr. A.U. Ubale sir, Joint Director, Higher Education, Kolhapur, and Dr. V.V. Kiledar, convener of the seminar, head of the Department of Physics, Shahu College, Kolhapur. Today's national online seminar on advanced materials and their applications is being attended by number of participants within the state and outside the state from various colleges and from various universities. And therefore, I think that this online mode of conducting the seminar is more effective you can reach to the most people with cost-effective ways. You need not have to register, you need not have to travel, you need not have to come over here, but you can listen online to the various well-known resource persons. One more advantage is that the resource person from IITs and NITs and very premier institutes in India and abroad are accessible through this online mode. And therefore, I would like to congratulate Dr. V.V. Kileda for organizing this national online seminar on a very important topic, which is advanced materials and their applications. As we know, advanced materials and applications is an interdisciplinary approach which involves the students and faculty members, teachers and researchers from physics, chemistry and even life sciences. And therefore, when all these three branches fuse together, the new materials take birth. And therefore, this particular conference is an interdisciplinary conference. The students and teachers from various backgrounds, they are attending this conference. As we know that advanced functional materials are very, very important for various applications because of their outstanding electrical, mechanical, chemical, optical and thermal properties. Moreover, the functional materials and nanomaterials, they also exhibit an outstanding properties because if we shrink the size of the material to the nanoscale, it can offer a very outstanding surface area to volume ratio. It can have a lot of outstanding properties, and we can harvest these properties and fabricate some innovative devices which are beneficial for the society. And therefore, we know that these advanced functional materials are being synthesized in various laboratories, and in a certain way, there are different ways of synthesizing these materials. Physical routes are there, physical techniques are there, and even biological synthesis methods are there. So all these physics, chemistry, and biology people can come together, they can invent something new. The new synthetic strategies are very, very important. It is also necessary to tailor the size of the material, and subsequently the properties will change. And therefore, you can use this material for the innovative applications by fabricating some novel devices. We know the materials like silicon, germanium, gallium arsenide, gallium nitride, even copper indium gallium sulfide, all these materials that are known to us for several decades. Silicon is the first material which is used for the fabrication of the electronic integrated circuits. This is because of the silicon that we can see the very large scale integration. Now all the mobile telephones, even computers, all these are because of the silicon integrated circuit. Because of the present sophisticated fabrication technologies, now it is possible to fabricate the transistors of the size, a very small size of say 5 nanometer to 10 nanometer. And because of which we can increase the packing density of the transistors and you can make a very powerful device. Germanium is also very good semiconductors. You can fabricate the transistors out of it. Gallium arsenide and gallium nitride are the materials which are used in the light emitting materials. They are light emitting materials. They emit light by virtue of their direct band gap energies. It is also very interesting to see the changes in the properties of the gallium arsenide and nitride when we shrink the size to the nanoscale. A lot of research work in the globe, they are working, researchers are working in the field of gallium arsenide, gallium nitride in the nanoscale. Solar cell materials are also very, very important. The well-known material is silicon, of course, because it can convert the light into electrical energy. But another material is copper, indium, gallium sulfide, or copper, indium, gallium selenide. These materials are useful in the solar cell materials. There are various forms like single crystal, polycrystal, and amorphous phase. And then the new phase came out, that is a nanocrystal. As we know, the credit goes to Sir Richard Feynman, who delivered a lecture in the year 1959 entitled "There is a Plenty of Room at the Bottom." His lecture envisaged the importance of working at the nanoscale. And now we have various nanometals like silver nanomaterials, gold, platinum, and palladium. Not only that, you can combine two metals together to have bimetallic nanoparticles or nanomaterials. Another important material recently has been found out is graphene. It is a two-dimensional material which has been invented by Sir Andre Geim and his student, and they got Nobel Prize for that because it is a very fantastic material with outstanding properties. You can find the application of graphene in almost all the applications. Only thing is that one has to synthesize, one has to produce graphene with a very, very high accuracy and precision. That is the challenge in that particular field. Recently, some researchers in the USA, they have invented another 2D material which is equivalent to that of graphene. It is amhexene. Amhexenes is a family of a material, two-dimensional materials, and they have properties similar to that of the graphene. There are other layer materials and low-dimensional materials like zero-dimensional, one-dimensional, and two-dimensional materials. There are various synthetic strategies people have developed in the laboratories, with the help of which you can synthesize zero-dimensional, one-dimensional, and two-dimensional materials. Then it is also important to look at this practical work through theoretical work. Theoretical simulations are doing, which is called as a combinatorial chemistry or combinatorial physics. You can simulate the properties of the material, what will happen to the properties of the material if you manufacture it at the nanoscale. All these things, you can sit in the room on the computer, you can simulate these properties. And if you find that particular property interesting, you go to the lab and synthesize that material. By the way of this, you can save a lot of time and lot of material and lot of. Recently, nanocoatings for various applications are coming up. So nanocoatings for UV radiations blocking, nanocoatings for antibacterial, antiviral coatings, superhydrophobic coatings, superhydrophilic coatings, oleophobic coatings are very, very important. And at the end, I would like to just tell you about the nanomaterials or the advanced materials for the battle against COVID-19. We all are facing the problem of coronavirus. COVID-19 is an outbreak. Across the globe. Coming up with some innovative ideas of killing the bacteria through materials, nanomaterials, advanced functional materials are being. Therefore, like a PPE kit, physical protection kits are being coated with antibacterial, antiviral coatings. Masks are being coated with antiviral coatings, and various textile materials are being coated with the help of some antibacterial materials coating. Not only that, our hospitals and dispensaries, they need such type of materials very, very badly, very urgently. And therefore, we should all come together and think about how we can develop the materials for the medical purpose, for the health purpose. This would solve the problems of the country. This will solve the problems of the world. With these few remarks, I again would like to thank Dr. V.B. Killedar and Principal Dr. S. Sarwaki for inviting me here as a chief guest. And I would like to wish all the participants very best. Let this particular conference be very, very informative, fruitful, and rewarding. There are resource person from Pune University, Professor Sartari, Indian Institute of Technology, Indore, Professor Shirge and Dr. Rupesh, they will definitely give a larger insight into what I told you and what I give you something in the introductory part. Thank you so much. Thank you.
Thank you very much for setting up the right platform for the further deliberations, sir. Now I request Dr. Kileda, sir, to introduce the keynote speaker, Dr. A.U. Kubare, Joint Director, Higher Education, Kolhapur Region, to address the participants.
Good morning, friends. Now I introduce the today's keynote speaker, Honorable Dr. Ashok U. Ubale, physicist and well-known researcher. He has recently joined the Office of Joint Director, Higher Education, Kolhapur Region. Before this, he was working as Associate Professor and Head, Department of Physics, Government, Vidarbha Institute of Science and Humanities, Amravati, Maharashtra. He completed his MSc and PhD from Shivaji University, Kolhapur. He has a teaching experience of 24 years. He has published 5 books and 1 patent. He has a research experience of 24 years. He completed 3 research projects sanctioned by NGOs and GOs. His number of PhD students completed PhD under his guidance is 6. Number of MPhil students completed under his guidance is 11. Now, 5 students have been registered under his guidance for PhD degree. He has published more than 95 research papers in national and international level journals. He has participated in 35 conferences, symposia, seminars, and workshops at national and international level. He is a managing editor of Vidarbha Journal of Science. He is a editorial board member of International Journal of Materials, Chemistry, and Physics. He is a member of Board of Postgraduate Education in College, SGB, Amravati University, Amravati. With this brief introduction of Honorable Dr. Ashok Ubale, sir, I request the today's keynote speaker, Dr. Ubale, sir, to guide the participants. Thank you.
Thank you very much, sir. Next, Dr. A.U. Ubare, sir, to address the participants.
Respected Dr. S.T. Salunke, Principal R.C. Shahu College, Kolhapur, my Guru, respected Professor P.S. Patil, Dean, Faculty of Science, Shivaji University, Kolhapur, my friend Professor S.D. Sartare, Associate Professor, Savitribai Phule, Pune University, Pune, Dr. P.M. Shirge, IIT Indore, Dr. R.S. Diwan, IIT Indore, convener of this seminar, Dr. V.V. Killedar, IQAC coordinator of this college, Dr. S.M. Sathe, and all faculty members of this college and dear participants. Friends, first of all, I must say thanks to Dr. Sathe sir and Dr. Killedar sir for organizing this seminar and inviting great personalities from physics. That's why I am sure that today's seminar will be a golden chance for participants to update their knowledge. We know that remarkable advances in structural materials technologies have been made in the past 25 years. New structural materials such as metals, semiconductors, ceramics, polymers, and hybrid materials called composites have opened a promising avenue in manufacturing industries. Their superior properties offers the opportunity to design more compact products with greater fuel efficiency and longer life. The present seminar may have discussion on some of these aspects of advanced materials with particular emphasis on applications in various types of optoelectronic devices. Generally speaking, it takes a long time before a new material can be put to practical use. Research of materials is merely the starting point for the research and development process. specifically new substances developed from research on existing substances while searching for new functionality. Out of these new materials, the materials which are socially and economically useful attracts the researchers from various fields. Friends, even in 2020, materials research can be placed as a key technology for cutting-edge industries that take the initiative in building a sustainable society. Also, by 2020, it is expected that the whole world will enter into an age of grand economic competition where materials industries will play key role. At present, there is high competition in the highly industrialized countries in the semiconductor electronics, information communication, energy and life science industries. Thus, in order India to maintain and improve the competitiveness, it is necessary to improve our basic research and fundamental research and development to the development of next generation technology and the creation of new materials. I wish all the best for today's event. Thanks. Thank you very much.
Thank you very much, sir, for your inspiring words. Now we are moving into the first technical session of the webinar. We are graced with the honorable presence of the person, Dr. S.T. Sartale, Professor, Department of Physics, Savitribai Phule University, Pune.
With
Dr. S.M. Sathe.
With great pleasure and pride, I would like to introduce today's resource person, Professor Dr. S.D. Sartale sir, who is currently working in Savitribai Phule Pune University as professor in physics. He obtained his PhD from Shivaji University, Kolhapur in 2002. Dr. Sartale worked as an Alexander von Humboldt Fellow, visiting scientist at Hahn-Meitner Institute, Berlin, Germany. Later on, Dr. Sartale worked as a research associate in National Central University, Taiwan, before he joined Savitribai Phule Pune University in 2008. He was NIMS postdoctorate fellow at National Institute for Material Science, Japan. Dr. Sartale was also invited to attend the Nobel laureate meeting at Germany. He is recipient of world-renowned Alexander von Humboldt and Japan Society for Promotion of Science Fellowship. Dr. Sartale is life member of different national and international bodies. He is Joint Secretary of Alexander von Humboldt Academy, Pune chapter. Dr. Sartale has about 90 research publications in reputed international journals to his credit. He delivered a number of invited talks on several topics in national and international institutes. He has produced 3 PhDs and 11 MPhils. He has completed 6 research projects of worth of about 1 crore, funded by different government agencies. He is also referee for different international journals. Ladies and gentlemen, Professor Dr. Sartale.
Thank you very much, sir. May I request Mr. Sartale to share his views?
Yeah.
Sir.
Yes. Is it? It's coming? Yeah. Good morning, all. Am I audible? Yeah. So good morning, all. It's my great pleasure to be part of this webinar on this advanced materials. At the outset, let me thank Dr. Killedar, convener of this webinar, principal, sir, and all the organizing committee member for organizing this particular webinar, which is very useful for many researchers working in the advanced materials. Today I'm going to talk about this importance of noble metal nanoparticles in search detection. Obviously, as already Professor Patil and Dr. Ubale sir has discussed about the importance of these nanomaterials, basically advanced materials. I'm basically restricted my talk only to metal nanoparticles. Let's first, discuss about what is spectroscopy and basically light. So whenever we incident light on any material, there are different processes happen, like reflection, transmission, absorption, scattering. I'm in this particular talk, I'm interested in scattering. Obviously, reflection, transmission, absorption can give me different types of information about that material. As far as scattering is concerned, we know that there are two types of scatterings. One is elastic scattering, which is called Rayleigh scattering, and the another one is inelastic scattering, which is also called as Raman scattering. So this is something, I have to this. We know that the first scattering was discovered by Compton. He actually experimentally observed and theoretically proved that when an X-ray or basically gamma rays or high energy photons incident on an electron, what happens that the photons get scattered, and that's energy after scattering, the photon loses its energy and the wavelength is increased, which is by this the formula he has given that it depends upon the angle of scattering. And when this news came, what happened, this Raman, our Professor C.V. Raman told that to his student or colleague Krishnan that, okay, if it is possible with X-ray, it should be possible with light. And he planned the experiment. And what we know that, on this 16th February 1928, he actually wrote to Nature that we will be possible, possibly we can observe new radiations or the radiations with different wavelength or frequency than this radiation. On 27th, they wanted to perform this experiment, but somehow it wasn't possible. On 20th February 1928, they actually saw this Raman spectrum, and therefore we also celebrate that day as a National Science Day. And then on 29th February, it was sent to the Associated Press. This particular discovery was actually rejected by a referee because the referee was not convinced. However, it was published by the editor, and we know that in 1930, C.V. Raman got the Nobel Prize for this great discovery. This was the instrument Professor C.V. Raman used, which has actually they use the sunlight, which is they use these two lenses and two filters, and this is the first Raman spectrum they published, where you can see that when you use different filters, then you can see that these are the different lines which were observed, and Raman said that this is because of the inelastic scattering. So there was change in the wavelength, and this is something you can actually see. Okay, so then, but nowadays the modern Raman spectrometers, obviously that was the first spectrometer Raman has used, where he has used the sunlight as a source of light, and he used normal filters and lenses. It was okay to just to demonstrate that, okay, there is some inelastic scattering occurs due to the molecular vibration. However, now the research demands very advanced, sophisticated Raman spectrometers, and this is something like the Raman spectrometer we are having in our department. This is made by Renishaw, the British company, which essentially uses the lasers of different wavelengths. Like you can have red, blue, and different types of lasers. So different wavelengths can give you different types of information, and there is a microscope. This laser will incident on your sample, which will get scattered by the sample, and then it will pass through this filter, which will essentially filters the the Rayleigh scattered rays, and it will give you the intensity of the inelastically scattered laser with respect to wavelength or frequency or wave number and so on and so forth. So that is what something like we have. This is the Raman spectrometer we require, the modern Raman spectrometer. The principle is same, where you incident a light on a sample, and the sample will, because of the vibrations of the molecules in the sample, there will be inelastic scattering. So let's try to understand how does this happens. I mean, this is a classical approach of this Raman scattering. What we know that whenever an electromagnetic wave incident on any particular molecule, it produces the dipole, and the dipole will oscillate with the same frequency as that of the electromagnetic radiation which is incident on that, and we get the elastic scattering. That is what we also call Rayleigh scattering. And the intensity of the scattered light, it depends upon this the dipole moment, which depends upon the polarizability of the molecule and the incident electric field E0. And obviously this is cos 2 pi nu t. So there are two factors which decides the the intensity of elastic scattering, is the polarizability of the molecule and the intensity of the electric field of the incident radiation. However, when we solve this equations, I mean there's something we do that, then, and if we these generic coordinates we introduce, what we see that there is actually there's three terms comes when we solve this equation. The first equation, like this mu, it depends upon these three factors. The first factor is where we are having only the polarizability and the incident electric field, and there is no change in
hello sir. Hello. Hello sir.
Hello. ऐकू येते ना? Okay, so what we see that there are three terms. The first term, it doesn't give me any change in the frequency, which is Rayleigh scattered. However, there are two additional terms comes where you can see that the frequency will be either increased by the vibrational frequency of the molecule, or the frequency will be like reduced by the vibrational frequency of the molecule. And this, there is another term which you can see that here is the change of the polarizability with respect to the generic coordinates. What do you mean by generic coordinates? I'm coming to that point very soon. So what we can see that there are two scatterings which you can see that one is Rayleigh scattering, the other one is Raman scattering. I mean, if I can just see the difference that there is in Rayleigh scattering, no change in wavelength or frequency. It depends upon E0 and it depends upon alpha naught. So, however, the Raman scattering, which involve these two terms, it is like the scattering frequency or wavelength or wave number, whatever it is getting shifted by the vibrational frequency of a molecule. It also depends upon the incident electric field of the the electric field of the incident radiation, and it depends upon not only the polarizability but change in the polarizability with the generic coordinates. So we know that there are different types of molecular vibrations. For example, you are having this symmetric stretching, asymmetric stretching, scissoring, and rocking, and all this sort of thing. So, like I wanted to tell you that the change in polarizability Q is the generic vibrational coordinate, because depending upon whether you are having stretching or bending and so on and so forth. For example, if you are having stretching, then it will be R. If it is bending, then it will be theta, and like that. So let's see, like there are couple of examples where we will see that how this alpha changes along with vibration for each mode. Let's say for the symmetric stretching, let the molecule is stretching symmetrically. What will happen? Okay, in the beginning the polarizability will be 0. If you stretch it, the polarizability will increase. Again, like the molecule, again you go back to your initial position, the polarizability will become 0. And again, if you compress it, then the polarizability will decrease. What we see that like this change in polarizability gives you the straight line. Obviously, the slope is not 0. So d alpha by dq is not equal to 0, and therefore these particular vibrations will be Raman active. However, if the stretching is not symmetric, let's say it is asymmetric, what will happen in that case? in the beginning, the polarizability will be 0. Okay. When you are stretching in this side, this will be, goes to this side. I mean, the polarizability will increase like this. And when you stretch to this side, the polarizability will be like this. And what will happen, essentially, you are getting a curve. And if you are getting a curve, the particular because the slope of this particular line or the tangent to this curve will be 0. What does it mean? It means that the asymmetric stretchings will not be Raman active. So there will be, like we have seen that, okay, there are these in classically we know that some of the stretching or vibrations will be Raman active, some of them will not be Raman active. From quantum mechanical point of view, what we know that, okay, there are different electronic states. It can be molecular states or the atomic states, you can say that. And what happens, like, okay, whenever the photon is incident, or the light with the sufficient energy, okay, is incident, what will happen? The electron will go to some virtual state, and what happens, like, it can come to the initial state. Then this will be, because there will be no change in energy, this will be called the Rayleigh scattering. However, what can happen, like instead of because the electron is going from this state to this state, instead of coming back to this state, it can come to this can come to this particular point. So what will happen, like there will be decrease in the energy or increase in the wavelength. Similarly, what can happen like this, when the photon is, the electron is coming to this higher state, instead of coming to this, initial state, it can come to the, even, lower state, and there will be an increase in the energy. So what will happen, like you can see that quantum mechanically also, you can see that it depends upon from which electronic state the electron got excited, and when it comes, where it comes back to, whether it is original state or to the lower energy state or to the higher energy state. Accordingly, you will get the change in energy of this scatter, which is we will call Raman scattering. When there is a decrease in the energy, then we call those lines are called Stokes. And when there is increase in energy, those will be called anti-Stokes. So we will be having like Stokes lines, Stokes and anti-Stokes. These are the two Raman scattering. And like I already told you that this will be like, incident radiation, this Rayleigh scattering, and there will be Stokes, which will be at lower energy, means lower frequency, and there will be anti-Stokes, which will go to the higher energy, which is what we call anti-Stokes line. And naturally, we can see that the probability of emission is nothing but, obviously, proportional to the observed intensity. If you are having more intensity, it means that the probability of that particular scattering or emission is higher. That's what the basic principle of spectroscopy. So like you can see that the emission, like the Rayleigh scattering, is the probability is very, 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 very high as compared to Stokes, and the Stokes probability is higher than anti-Stokes. So of course, you can find out from Maxwell-Boltzmann statistic the intensity ratio from the Stokes lines and anti-Stokes line, which I'm not going to discuss right now. What we can say that this is what we typically see the Raman spectrum. We usually plot on the x-axis the Raman shift. Okay, and the Raman shift means this is the shift which you can usually we show this Raman shift in terms of wave number, but you can show in terms of wavelength or frequency or whatever it is. So because all are related with each other, I'm sure all of you know about that. So whenever there is no change in the energy, this is what we are having, this Rayleigh scattering. And if this is like the shift is negative, means there is increase in the energy, these are the anti-Stokes lines. And on this side we are having this Stokes line. So usually Raman spectrum is shown in with the Raman shift, positive shift. So we are having only the Stokes lines. We never start, usually it doesn't start with 0, because at 0 there will be very huge intensity because it is Rayleigh scattering. So we start with 200 or so and so forth, with the higher Raman shift like 400 or whatever, 4000, depending upon 2000, depending upon that the range, and your spectrometer allows you that particular range. So like this Raman spectroscopy is very, very important, and it has a lot of applications. Why? Because this Raman, we have seen that every molecule has its characteristic modes of vibration, and those vibrationals are unique for that particular molecule, and we know that some of these vibrations are Raman active, some of them are not Raman active. But suppose like those vibrations are Raman active, then what we know that these vibrational modes gives you characteristic Raman frequencies or characteristic Raman peaks. So this you can tell you that okay, whether that material is like, for example, like a very well known example is diamond and graphite. When you are having diamond and graphite, you get very different peaks for graphite and diamond. So I can easily tell that whether this carbon is in the form of graphite or diamond. Or you can, for example, you are having TiO2, then I can easily tell that whether it has annatase phase or rutile phase. So it has like the fingerprint of that particular material. If there is any change in the Raman peak, what we can say that obviously like I can get some information that this particular material is there's some chemical interaction, there is some stress, strain, or there is some temperature is increase or decrease, and so on and so forth. And of course, from this, like if the intensity of some peaks are increasing or decreasing, I can see that the symmetry of that crystal is different in that particular direction. From the width, I can see that the size, shape of the nanostructure, whether this is nanomaterial or microcrystalline material, the peak width will be different for this different morphological. And also, of course, from the intensity, I can see that the amount of materials or film thickness. For example, if I can say that whether my thickness is increasing or decreasing, and so on and so forth. So it has lots of applications. Very important that all this like the applications does not demand me in a preparation of the sample. This can be used as a solid, liquid, and gaseous, and therefore in forensic sector it has a lot of application because it does not destroy the material. I have to just put like X-ray diffraction. I have to just put the material over there and take the Raman spectrum, and I can do it. And I require very small amount of material, and therefore it is a state-of-art technology for characterization of material. So after this, all this, the good things about this Raman, obviously there are some certain limitations. Like what we have seen that whenever the light is incident on samples, there are two types of scatterings occur. One is Rayleigh scattering, the other one is Raman scattering. And Raman scattering can, it basically, it's a change in energy, either positive or negative, and accordingly we have seen that is Stokes or anti-Stokes line. The most difficult part of this Raman scattering, and therefore we require very advanced Raman spectrometers, is the reason is that most of this like this whatever radiations fall on the materials, they do this Rayleigh scattering. I told you that the probability is very, 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 very high. So out of 10⁻⁷ counts of the Rayleigh scattering, there is only one count comes for the Raman. And again, for anti-Stokes, it will be even smaller. So therefore, usually, as I already told you that the Raman spectrum is shown in the for Stokes line. So the Raman scattering is very weak. So if I want to, and there is also a problem of fluorescence. Whenever we are having Rayleigh scattering, along with Rayleigh scattering, there is a fluorescence background. So for fluorescent molecules or some other molecules, it is also difficult to get the Raman signal. And if I want to do, for example, the trace detection, means if I want to have very small amount of material, I want to detect using this, then obviously I will be having problem. Why am I having problem? Because the Raman scattering is very big. So then what happens, like even though in 1928 this Raman discovered this Raman effect, it was not widely used because because first thing is that the Raman active modes has to be there. If those Raman active modes are there and the amount of material is very big, then what will happen? I would not able to see the Raman's spectrum of that particular molecule. It was an accidental discovery in 1974. What happens, like the people were, one group wanted to discuss or wanted to study the Raman scattering of pyridine on silver. And what they did, they actually, they did some electrochemical treatment to the silver surface. And because of the electrochemical treatment, the silver surface was, getting rough. And what they saw that if there is no treatment to the silver surface, I couldn't get any, peak for the this pyridine Raman peak. I'm supposed to see at this particular position. But when they, make this rough surface, they saw that, like this, some certain peaks appears, which are, which belong to pyridine. So they were, like, it was a very curious thing that why this, like the pyridine, otherwise I would not able to observe. I can observe whenever, the surface of the silver electrode is rough. And then, 1977, there was a lot of debate started. People started to discuss about that, whether it is because of the roughness, whether it is because of the, can we observe for any metallic surface? Can we observe it for any oxide surface or say any other surface? And so on and so forth. And people actually come to know now, I mean, we are in a position to know what, and that is particular, that Raman scattering, what we call it, surface enhanced Raman scattering. And that's what I'm going to talk today. That's what I said, that SERS is the surface enhanced Raman scattering. The surface enhanced Raman scattering, there are two mechanisms basically which are responsible for enhancement in the Raman signal, what I already showed you, where they put the pyridine molecule on a silver surface which is rough, and what they saw that the Raman signal of pyridine molecule got enhanced very much when the surface was rough. And now we know that there are two particular enhancement mechanisms. One is what we call electromagnetic enhancement, the other one we call chemical enhancement. So electromagnetic enhancement is what, when we are having this, that, and now we know that the silver is basically the plasmonic metal, where you are having this surface plasmonic resonance occur in the visible region. Okay, so what happens, like whenever the light falls on these particular noble metals, what happens that they start to oscillate with certain this plasmonic resonance occur in the visible region. And if the electric field of the electromagnetic wave coincide, or which is close to the this resonance frequency or resonance frequency of this particular plasmonic nanoparticles or rough surface, what happens, there is an enhancement of both. The electric field is getting enhanced, as well as whatever the Raman signal you get, that is also getting enhanced, and therefore we get the enhancement in the Raman signal, which is like basically, which is too much. Theoretically we can enhance the signal by the order of 10⁻11 to 10⁻12 times. Of course, there is another enhancement is responsible for this. The other enhancement is like we are having this, what we call the interaction of the molecule with the surface of the metal surface, where we call this is chemisorption. We know that there is physisorption and chemisorption. So whenever there is a chemisorption, there is a charge transfer between the molecule and the metal surface, and this charge transfer is also responsible for enhancement in the Raman signal. But however, this chemical enhancement is it's not too much. It is only of the order of 10⁻2 to 10⁻3. However, electromagnetic enhancement is huge. It is of the order of 10⁻11 to 10⁻12. So we are aware that like this the major factor deciding this in the surface enhanced Raman spectroscopy is localized surface plasmon resonance. All of you are aware of that. Whenever, as I already mentioned, that whenever the light is excited, white light having different frequencies, it is excited on this metal nanoparticles. What happens? There is only because of this plasmon is oscillate with the certain frequency, and you get a very high intensity of at certain frequency or certain wavelength. If the incident wave, the laser, has the same wavelength, what will happen? There will be enhancement in the signal. And that this particular LSPR phenomenon is used to synthesize this silver nanoparticles or gold nanoparticles of different colors by changing the size and shape of this particular nanoparticle. So as I already mentioned that, okay, whenever this is particular, you are having this surface particle or this metal nanoparticle, this is the molecule. What happens? This particular electric fields are coinciding with each other because both are having same frequency. And what we have already told that, we have already seen that the intensity is proportional to the this electric field dipole moment. Okay, induced dipole moment. But however, this mu depends upon the polarizability and electric field. Now, polarizability is, of course, we have seen that in case of Raman scattering, the polarizability need to change with the generic coordinate, and that decides which modes are Raman active and which modes are not Raman active. So anyway, those Raman active modes are there. So this polarizability is not in our hand, because that decides by the molecule and how this molecule is vibrating, whether it is symmetric or asymmetric. That's what we have seen. However, what we can see that this electric field is either I can change the intensity of my incident radiation. So one way what I can do, that I can increase the intensity of my laser beam. However, we are aware that if I increase the intensity of my laser beam, it can damage my sample, especially for biological samples or some polymers. So I have limited, I have to, there is some limitation. I cannot increase the intensity of laser beyond certain limit. But I can, because of this, this plasmonic nanoparticles, this electric field is getting enhanced, and therefore I am getting increase in the intensity. So this particular surface, like SIRS, has lots of application. And now, and I already told you that it started in 1977, and now people have developed this SIRS up to the level that you can now detect single molecule using SIRS. Okay, so you can detect the single molecule. You can detect, for example, I'm going to discuss this. You can detect this melamine in this food allergens. You can discuss, these dyes, these pollutants molecules. You can discuss, you can detect this, all this viruses, biological. You can, for example, it is useful for this cocaine and this, these drugs. It can be, even used to detect these HIV viruses. It can be, used to in vivo glucose measurement. For example, somebody has sugar or not, and it can be, this, as I said, that methylene blue means these pollutants, and it can be, this molecular and cellular analysis. So, like I have just choose some of the typical examples to show you that, or to convince you that SIRS is highly now it is very, very useful technique, and many groups in the world, they are developing this SIRS. So what I have to do, I have to SIRS substrate. They are trying to understand theoretically how this enhancement is occurring, and both this theoretical and practical, experimental works are going hand in hand, and now people are getting this SIRS enhancement of the order of, like what we are expecting from the theoretical point of view. So how does it works? This is a very simple way. When I want to do this SIRS measurement, what I have to do, I have to have a rough surface, like we have seen in the first paper, but now what we are having this metal nanoparticles of the desired shape and size, where the surface plasmon resonance is actually close to the incident radiation. And what we do, we absorb this molecule, okay, whatever the molecule we are interested to measure, and this molecule, when we absorb, then what will happen, we will incident the laser, and then what will happen, there will be excitation of these plasmonic nanoparticles, and this will actually enhance the electric field, and this will give me the intense or enhancing the intensity will be enhanced in the Raman spectrum, which will be, we call the surface enhanced Raman spectroscopy. This is in this cartoon. I will show you what we do in our case. For example, what we have, we use this rhodamin 6G molecule, okay, which is very toxic pollutant that many of you know. We want to detect this rhodamin 6G molecule in the water. Okay, so what will we do that? Okay, in the beginning, what I will do that this molecule I will put on this surface of any, let's say, glass or whatever, and then I will incident the laser, and then obviously what will happen, there will be Raman scattering, and this scattering I will detect with the detector, or the Raman spectrometer. What I will, you can see that if I'm having only rhodamin 6G, what I see that this intensity is almost zero. You can see that it's a very noisy spectrum. So you cannot say anything about that, whether there is a RE60 any molecule or not, because all this is noise. But if you put this particular rhodamin 6G on, let's say, this silver nanoparticles or gold nanoparticles, where this surface plasmon resonance occurs close to this incident wave, what will happen in that case? the Raman signal, you can see that earlier we were having this 0 intensity. Now it becomes almost, like 80,000. So from 0 to you can get 80,000 intensity. So it is very useful. You can immediately see that. So the molecules otherwise I could not able to detect if I put it on any surface, because like there is a fluorescent background. Now this fluorescent background will get suppressed and I will get very high intense Raman spectrum, and I can now easily study this Raman spectrum, and I can tell whether this RH6G, I can see the intensity change with the concentration and so on and so forth. So a systematic study can be done. So if I want to, like as I told you that, okay, this is something like we are having search. What I have to do, I have to develop or I have to code this metal nanoparticle on certain surface, and then I will absorb that the probe molecule, whatever the probe I am having. It can be the pollutant, it can be like adulterant, or it can be virus or whatever it is, and then I have to get the enhancement. Now the thing is that this enhancement is very critical, depends upon the size of the metal nanoparticle. For example, I am having this metal nanoparticles. These colors tell you the electric field around that particular metal nanoparticle after incident of the laser. So when I'm having, this laser is incident on that particular metal nanoparticles, what is happening? There is an enhancement in the electric field. And these numbers, what you can see that these numbers tells you the enhancement or the electric field. This is, you can see that when these two metal nanoparticles are close with each other, when the distance between these two is 2 nanometer, the electric field is of the order of 10⁸. If you are going, just come here, okay, from when the distance is slightly higher than the 2 nanometer, what you can see that the electric field decreases to 10⁵. So there is a 3 order of magnitude decrease in the Raman signal. I mean electric field, and obviously that will result in the intensity reduction of the 3 order of magnitude. So what does it mean? That I have to have this metal, I mean this the probe molecule need to be very close to the metal nanoparticle surface. Now what does it mean? That if these 2 nanoparticles are merged with each other, what will happen? If they merge with each other, then the probe molecule will not be in contact with this, and then obviously we will see that if the particle is getting bigger, the plasmonic the LSPR, the surface plasmonic resonance peak, will also occur at different position, and therefore you will not get that much enhancement. So the first thing is that what we have to see, that only the metal nanoparticle, the probe molecules which are in contact with the surface, those only get enhanced. And therefore what we say that this in search, there's a very nice term we call the hot spot. Hot spot means what? The spot where this the probe molecule is in contact with the metal nanoparticle. Another thing what you can see, that it's not only that the enhancement depends upon the size of the nanoparticles or the separation between the nanoparticles, but it depends upon the shape of the nanoparticles. For example, if you are having a spherical nanoparticle, then what you can see, that the electric field is restricted only to the surface, and whenever you are going away from that, the red color means higher electric field, okay, and the blue color means the lower. So when I'm going from yellow, red to blue, you can see that the electric field is decreasing. Similarly, if I'm having the nanorods, it will be only at the the surface to this edges of this nanopart. When you are having cubic, then at the edges you can have triangular shape, you can have the, for example, star shape. If you can make these metal nanoparticles of different shapes, you can get different surface enhancement, I mean this enhancement. But this enhancement will be restricted to only, for example, if I'm having this star shape, the enhancement will be only occur at this this only at this edge. So if I put my probe molecule here, then I will not get the enhancement. But if I put the probe molecule at the edge, then I will get a huge enhancement. So I have to decide. For example, if I'm having nanorod, only nanorods at these edges I will get the enhancement. This entire region is from the surface enhanced Raman spectroscopy point of view, is not useful, because this doesn't give me any enhancement in the electric field. So there will be no enhancement in the Raman signal. So there is a one thing like what we can say that we have to have. So if I'm having this, for example, spherical nanoparticle, they should be of the same size. They should covered without surfactant. I want to put this point here, very important, because why surfactant? In the earlier slide, we have seen that whenever the probe molecule is like away from that particular this metal nanoparticle surface, the enhancement is decreased, by, for example, if it is decreased, you are here, the enhancement is in decreased by 10 raised to 3 order of, or 3 order of magnitude. It means that if this nanoparticle surface is coated with some capping agent, usually you know that whenever you make a metal nanoparticle, in chemical synthesis, the capping agent actually restricts the size of the nanoparticle. So what will happen? The metal nanoparticle will be covered by this particular this capping agent. And what does it mean? That if you are having this the capping agent and then you put the metal this probe molecule, what will happen? This probe molecule basically is away from the metal nanoparticle surface, and therefore the enhancement will be lower. So I have to have a metal nanoparticle without capping agent to get higher enhancement. So if I want to get a higher enhancement, I should have the uniform size first thing, because then I will know that this hotspot, because if this this particular nanoparticle is of this size, and if there is another suppose these two nanoparticles form, they attach with each other and they give me this particular, for example, nanorod like shape, what will happen? Then I will have only enhancement only at this region, and this region will not, there will be no enhancement. So I have to have, for example, spherical nanoparticles. They should be separated with each other, and they should be of the same size, and there should not be any capping agent. Then I will get maximum enhancement. So what we did in our laboratory, and of course there are many approaches people have used, but I'm going to discuss very briefly about our approaches. We use this successive ionic layer absorption reaction method and spin coating. What is the advantage of this is what we have, like we can put the substrate on which we want to grow these metal nanoparticles. We immerse in the first solution of the metal nanoparticles. For example, if I want to grow silver nanoparticles, I will immerse this substrate, which can be glass, which can be like cotton, a paper, or anything. Advantage of paper or any flexible substrate and anything. We immerse in the solution of this cationic or metallic metal ion solution, where these metal ions will absorb, and we rinse them to remove all these loosely bound species. Then we put it in the reducing agent solution, in this case, for example, hydrogen hydrate or sodium borohydride, or like whatever suitable. And then we put it in again, we immerse or we rinse it, and then what we see that we see this these silver nanoparticles grow on this particular substrate. So the substrate, I already told you that it can be a glass, it can be paper, it can be cotton, it can be anything. And it's not only that you can grow only silver, you can grow silver, gold, and so on and so forth. So all these things we can do. I will show you some of the results. Another technique what we do is it's again similar to CLR, but what we do here, we put this metal ion solution on a substrate, and then we spin coat it. When we spin coat it, and then we get this metal nanoparticles, basically metal salt nanoparticles, and then we reduce them in either thermally or chemically, and we get this uniformly distributed metal nanoparticles. You can see that this is one typical SEM, where you can see that these metal nanoparticles are grown on very large surface. That is also important, because we have to, when we want to detect probe molecules of at different spots. So because if they are all uniformly sized and and with the same separation, I can take the search at here, this point, this point, this point, this point, this point, and everywhere I can go. And so I can the same substrate can be used for detection of very large samples, that is one thing. So like this is one typical result. I'm not going to show you that discuss in detail about our results because it is already published. So if you are interested, you can see. But what we can see that, okay, like if I change the cycles of the cellar, then what you can see that the size of the nanoparticles changes and their separation also decreases. They lose the spherical symmetry and they get kind of nanorod shape, because you can see that these two nanoparticles are merged with each other. And if they merge with each other, we this surface plasmon resonance, you get two kinds of peaks. The dipole we get whenever they are only the spherical nanoparticles. Hello. Okay. So these dipoles will give you that you are getting these dipoles when they are spherical nanoparticles. If they are not spherical, you get this quadrupole. And what we have seen that, okay, so this information is useful for us. What happens, like, okay, then this information, because we have seen that the surface plasmon resonance peak appears at different frequencies, and accordingly we can see that for 10 cycles you get very high intensity. This is 80K for this R6G. That's first. So from nothing to everything you can get. You see that for the when I put this this rhodamin 6G, a probe molecule, on glass, I get a 0 intensity. But if I put it on the silver nanoparticles, you get very high intensity. Similarly, you can if you don't have this the surface plasmon resonance, you can do the simulation, and from this simulation you can see that how much this electric field is increased. So you can see that this electric field enhancement for 1000 rpm, like this is spin coating, you get a very high enhancement. This is 9.98. It's up to 10 raised to, so 10 raised to 10. But if you are having, like, you go for 3000 and 1000, these are AFM images, you can see the enhancement is different. So what we have done, we can get this like the trace detection. So you can see that this methylene blue is a well-known industrial pollutant. What we can get that on, for example, if I put it on 10 raised to -1 molar on glass, you get 600 intensity. But even though very, very small amount of this pollutant is present in your water, 10 raised to -10 molar, see, still on silver nanoparticles you can get more than like 4 times higher intensity. So you can get for picometer detection also. This is very important. This is another point which we have to have for the Raman signal. I said the reproducibility. If you are having this Raman search substrate, if I put this dot here, 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 and at random positions, and if you see the Raman intensity, if it is more or less same, then we say that it is a reproducible Raman signal. So if you are going to make this search substrate, means you are going to grow this metal nanoparticles, this one factor you have to see, that it should be homogeneous and reproducible at different spots. Not only that, you have to have this repeatability. Means what does it mean? If I make for example, if I make the cellar for one slot, if I make this another slot, third slot, fourth slot, and so on and so forth, and do I get the same intensity? If I get the same intensity, and then you can say that your process is repeatable. So this is repeatability is also important factor. We can see that this as a signal is almost same. This another thing is, like, people want to know that, okay, can I use the same the search substrate for repeated reusable? Can I reuse? It's not possible because it depends upon whether your molecule is chemisop or phygisop. If it is like, for example, this chromic red is another pollutant. What happens, like, when I wash it with the water, then I don't get any intensity. So then if I again put this this probe molecule, then again I get this intensity. Again I wash it, again I get it. So it means that there is only electromagnetic enhancement, there is no chemisoption. However, if the molecule is chemisop with the these nanoparticles, what will happen, like, if I detect this, okay, there will be this intensity. If I wash it, only this like the electromagnetic enhancement and this chemical enhancement, because there is a chemisoption, So this molecule, I will not able to wash it, and therefore there will be some intensity. So for this particular molecule, I cannot use my surf substrate repeatedly, like I cannot reuse it. However, if the probe molecule is not chemisoft, it is only physisoft, I can reuse it. So this is one example. I would like to show you. So what we can do that, if I want to use it reusable, what I can do that, I can grow this silver nanoparticles, or for example zinc oxide. Now these silver nanoparticles, when you grow on zinc oxide, it is useful, because these hot electrons are formed. Hot electrons means this surface plasmon resonance, which increases the surface surf activity or surf performance. And then what happens, like these silver nanoparticles give me the higher intensity. How this you can see that, for example, if I'm having this, this silver nanoparticles grown on, this zinc nanorods, let's say, these are, like zinc nanorods. You don't see when you incident the laser. What you can see that there is no no electric field, because this zinc oxide has a very large band gap as compared to the visible radiation, because that this has the band gap is in UV. But when you are having these silver nanoparticles, what you can see that at this interface, the enhancement is too much. You can see that from it is almost 10⁶ times. But what happens like this, when you are having this this silver nanoparticle, like what I do, okay, I make this methylene blue, I have detected. Then when I put these UV radiations, all of you are aware that like this zinc oxide is well known photocatalyst. I mean, zinc oxide, you can have TiO2 or anything which is photocatalytically active material. Then what will happen when you are having this the radiation having energy greater than the band gap? What will happen? These electrons will go to the conduction band, and there will be electron hole pair, and this there will be this radicals will form, and those radicals actually mineralize or decompose or degrade this particular probe molecule. And these probe molecules, if you are degrading, what will happen? Okay, like then I can reuse the particular substrate. But however, you should see that this UV light, because this light has very high energy, therefore it will not cause any plasmon resonance, so this will not disturb anything. However, only those probe molecules which will absorb on this surface, they will get degrade. And then what will happen? Yes, I can now absorb. For example, these are these metal nanoparticles coated on this zinc oxide or TiO2 or whatever this oxide structure, nanostructures. Then these probe molecules will be absorbed. I will measure, for example, and then this methylene blue, before UV clean, I will get this particular intensity. Then what will happen? Then I will use this UV cleaning. So what will happen? I will incident UV radiations on that particular metal nanoparticles coated on this zinc oxide or TiO2 nanotubes or whatever. Then what will happen? Then I see no intensity here. You see that this methylene blue intensity is almost 0. These are basic. These peaks are from the zinc oxide. And again, if I put methylene blue on that, what will happen? Again, I can use this, I can detect this methylene blue. So reusable substrate can be used by putting this metal nanoparticles on that zinc oxide or TiO2 photocatalytically active material. This is something like new things which you can do if you want to do research in this particular field. So I will just tell you very few things about this melamine. Is as a food adulterant in milk. All of you know that milk is very important for as a for you get lots of things like energy, calcium, vitamin, and this. However, what happens, like we know that earlier people were using this adulteration, and the well-known adulteration is water, and there is no problem. But now what happens, like this the commercial purpose comes here, and now the companies can do so many bad things. We must have heard that urea, formalin, detergent, alkaline, and so on and so forth. So this melamine is added to milk to increase the protein content, because you know that whenever I want to see the milk is good or bad, we know that there is a fat level, in all our whenever I want to get the milk, you know that buffalo milk is good as compared to cow milk because the fat is higher, so the protein content is higher. And so what we say that, okay, the protein content is higher, so the milk is good. So melamine, which is otherwise used for, we know that melamine did dinner sheet, and there's melamine used for on the coating and so on and so forth. The same melamine people use it for the as a adulterant to increase the protein content of milk. So it is in actually the whatever the techniques you are having to check whether this milk is good or bad, those techniques will be like the this melamine actually give you the wrong reading of protein, and you can say that, oh right, I mean this milk is good because it has higher protein content, so I should get this milk because it has higher protein content. So obviously this is not permitted additives or food ingredient. So there nobody was even thought about melamine somebody will add in in milk to increase the protein content. So but what happens, like there was a scandal happen in China. 1 minute. Sir, don't. So what happens, like in 2008, like many people, I mean many 6 babies died, and 3 lakh people, basically 54,000 babies were hospitalized because it was a this baby food, it was melamine, and almost all the milk products were destroyed in China. And you can see that the stores were like empty. Then therefore like in our India also recently, in 2016, now we are having that this melamine should be like there should be some limit. If it is not, then you will get punishment, and that punishment is severe, we know that. So this bill is there now, you can have this life imprisonment and and huge fine if you find that you are selling the milk with melamine. So how do, I mean, because I already told you that the routine techniques what we are having, those techniques are not useful because those gives me the protein content, but this melamine actually increases the protein content, and therefore it is not possible. So what happens, like we can take the SIRS is very useful in that case. What you take this adulterated milk, okay, and then you centrifuge, and then you find out this milk suspension, and you put it on the SIRS substrate, and you can see that now here, see, this is the milk, okay, normal Raman spectrum, you don't get any signals. However, if you put this this adulterated milk on this SIRS substrate, then you can see get a huge enhancement, and it is only very small amount of melamine we have added, which is even below the limit of decided by FSAI. The same thing, and I'm finishing it in 2 minutes. Then there's not only that, because for example, like people can, I mean, you can use this on this there's pesticides which are because we know that this pesticides we spray on the fruits, but if we eat these pesticides, it is a very dangerous thing for us. So what happens, like we can coat these metal nanoparticles on this adhesive tape, and this adhesive tape we can paste on this particular surface of the apple, for example, in this case. Then all these pesticides will be like pasted on this tape, and then we can take the surface enhanced Raman spectroscopy of this. People have shown this not only for apple, for different types of fruits it is possible. It is also useful for all like these viruses and all. I already told you that. For example, I mean because already Professor Patil discussed about this. Since like we are meeting with we are discussing on virtually because of this COVID-19. So I thought whether this search is useful for search. Yes, it is useful. You can see that of course this paper is from the Chinese group, and they say that it is not reviewed, but this is an archive where they have shown that this COVID-19 samples can be detected with SIRS. So yes, I mean there is a possibility that this SIRS can be used for detect. I mean it's useful for this this COVID-19 swab. Whenever you collect that swab and if you put it on this SIRS, you can immediately get the signal. So I would like to conclude here. what I say that, okay, these noble nanoparticles like silver, gold, these can be used as a substrate for trace detection of environmentally toxic dye. Like I already shown you some results like the rhodamine 6G, methylene blue, and so on and so forth, as well as food adulterants and harmful pathogens like for example, COVID-19. So, but what is more important? We have to make this robust, repeatable. Robust is of course because it should be, like cheap. It should be we can handle it very easily. The synthesis process should be cheap. Then repeatable means I should, if I make whatever the synthesis process you have developed, if I can use, I mean, I synthesize one slot of that particular cell substrate. If I make another slot, I should get the same result. On that cell substrate, if you are having a large substrate, I can put a very small drop of my sample. So if I put it at different spots, I should get the reproducible result. And it should be reusable. I already shown you that you can make this reusable surface substrate by just by washing, but it is not possible for all the probe molecules. You can coat these metal nanoparticles on photocatalytically active materials, and using this UV cleaning, you can use them as a reusable substrate. Of course, this all these these 4 R's, I can say that robust, repeatable, reproducible, reusable substrate have huge potential. So I thank you for all of you for your kind attentions, and this is something, our work was published in this local newspaper Sakal, and I thank.
Thank you very much, sir. There are some participants who would like to ask the questions in this session. First of all, I call upon Prem Kumar's question. What could be the reason of the broadband's appearance while going from high concentration to low concentration of R6G on SERS active substrates? Over to you,
Can
sir.
you repeat, please, madam? Please repeat the question.
What could be the reason of the broadband's appearance while growing from high concentration to low concentration of R6G of SERS active substrates?
Okay. So I think I would like to go to that slide. I think they want to discuss this slide one more time. See what is happening here in this case. If I understood whatever that question is, well, I already told you that for 10 cycles, the intensity is higher because the surface plasmon resonance peak is actually matching with the wavelength of the incident laser. So the whole thing is here what? If the incident radiation energy or wavelength or frequency matches with the surface plasmon resonance wavelength, then we get the huge intensity. So otherwise we don't get it. So therefore that's how we have to optimize the the size and shape of the metal nanoparticles, where the surface plasmon resonance matches with the incident laser.
Okay, thank you, sir. Raghunath Patel's question is there any specific experimental procedure to enhance Raman scattering in the sample? Because 1 in million is 2H4 scattering, is Raman scattering, sorry.
Right, I already told you that the Raman scattering is very, very weak. So obviously if we want to enhance this, we have to go for this surface enhanced Raman scattering. That is the only way, because you cannot, whatever the probe molecule you are having, that probe molecule has its own cross section. I mean, I have not discussed about that, but the theoretical calculation, from theoretical calculation, we can tell that this particular mode of this vibrational mode has this cross section. Cross section means the probability. So not all the Raman modes will be, like most intense. Some of the Raman modes will have more intensity. Like for example, in this case also you can see that the Rhodaman 6G, only this particular mode has higher intensity. Naturally, it means that this particular mode is, the probability of, Raman scattering from this particular mode is higher. So only thing is you can increase the intensity by using this surface plasmon resonance. So by choosing the suitable metal nanoparticles or metal nanoparticle surface where the surface plasmon resonance will match with the incident radiation, you can increase the intensity of Raman signal, because there is an enhancement in the electric field of the incident radiation. No, I can't hear you.
Thank you very much for the scholarly presentation, sir. Now let's proceed towards the second technical session, for which I now request Dr. Archana Patil, Assistant Professor, Department of Physics, to introduce the resource person of this session, Dr. P.M. Shirge, Associate Professor, Discipline of Metallurgy, Engineering and Materials Science, Indian Institute of Technology, IIT Indore. Over to you, ma'am.
Good afternoon, all the participants. I am Dr. Archana Patil, Assistant Professor in Physics. I am here to introduce you with today's resource person, Dr. P.M. Shirge sir. Dr. Shirge sir is working as an Associate Professor, Discipline of Metallurgy, Engineering and Material Science at IIT Indore. He received the Master and Doctoral degrees from Shivaji University, Kolhapur. He has served as Dean Planning, Head, Discipline of Metallurgy Engineering and Material Science, Chief Warden of Hall of Residence at IIT Indore. He was visiting fellow at TIFR Mumbai. He worked as senior scientist at National Institute of Advanced Industrial Science and Technology, Tsukuba, Japan. He is an author of over 200 peer-reviewed research papers with 4,000 citations and H-index 34. 11 students completed PhD under his guidance, and 34 students completed their master thesis. His research group consists of 2 postdocs, 10 PhD students, and 6 master students. He is recipient of highly prestigious medal from Material Research Society of India in the year 2020. Dr. Shirge has spent an early career life as a scientist at Korea Electrotechnology Research Institute, Changwon, South Korea. He received a prestigious JSPS Fellowship of AIST, Tsukuba, Japan. Dr. Shirge has discovered several superconducting materials. The research interests of Dr. Shirge include areas such as electrochemistry, thin film growth, utilization of high pressure to synthesize novel materials, novel superconductor search, isotope effect, point contact spectroscopy, microwave studies, nanomaterials for solar cell applications and energy storage, gas sensing, etc. His fundamental contribution in the field of physics is to understand the basic mechanism of superconductivity by studying the isotope effect. He won MRSI medal in the year 2020, Excellence in Teaching at IIT Indore in the year 2016, Japan Society for the Promotion of Science Award from Japan in the year 2006, MEXT Fellowship in the year 2008 from Japan, Mekno 21 Award from Ministry of South Korea in the year 2004, Visiting Fellowship from TIFR Mumbai. He received Best Paper Presentation Award from Materials Research Society of India in the year 2000. He is the Fellow of Institute of Physics, UK member of Executive Body of Indian Scientists Association in Japan, on editorial board of the Open Applied Physics Journal, Bentham, reviewer for APS, ACS, JPS, IOP, elsewhere journals. He has visited, delivered invited lectures, attended conference, and chaired scientific sessions in several countries, including Japan, South Korea, Turkey, Greece, Belgium, France, Italy, China, etc. Thank you.
Thank you very much, I'm Dr. Shirge from IIT Indore. It's already introduced. Okay. I'm very much thankful to the Professor Khiledar for providing me this opportunity to present here by webinar. Okay. So before starting my lecture, I would like to thank IIT Indore because it's ranking 10th position national wise. Are you able to hear me? Just raise your hand.
Proceed.
Okay, thank you. Just somebody joining that waiting room is coming here. Waiting room. Okay. So today I will talk about the advanced functional materials for multifunctional applications. Okay. So basically I will give an introduction about the work which I have carried out, and then what type of work we are carrying out and what are their applications and how to prepare the materials, how to characterize and how to know which material, all these things, some basic stuffs I would like to introduce to you. Okay, before proceeding to the main content, so 11 PhD students, they completed PhD under my guidance. This is a research group. This is last year's photograph. And currently 7 PhD students, they are working under my guidance. Okay, this is this year's MRSI award, which I received from Materials Society of India. So there are 23 IITs all over India. Okay, and IIT Indore is the second generation IIT. Before that, only 5 IITs were there: IIT Delhi, IIT Kanpur, IIT Kharagpur, IIT Bombay, and IIT Madras. And in second generation, new 7 IITs were added. One of them is IIT Indore. Within 10 years, IIT Indore has ranked 10th in the position, and this is the area of the map of our IIT Indore, how it will be developed. This is a planned map of the IIT Indore. As I mentioned, IIT Indore has ranked 10th position in national wise in just 10 years, and we are doing good in research as well as in teaching. So in international level, it's ranking in the block of 351 to 400, and even in this category times ranking, we are at the second position. So this is my research group. Just I introduced about this one. Okay. So in IIT, being in IIT, we have to take a lot of courses. So these are the courses which I have taken. I've developed and taught these materials for devices, thin film and devices fabrication, then a lot of courses for the BTech, MTech, PhD students. Okay. So I have conducted 4 GAN courses. Just I'm giving 2 important one. I've conducted 1 GAN course with my earlier supervisor, Professor Akira Yu from Japan, on high pressure cylinder materials such as torque treasures and hints, because this is a very important topic for material synthesis. And because of this, I could discover a few new superconductors I will show in next slides. Then my research activities basically consist of these superconductors, magnetic nanoparticles, batteries and supercapacitors, sensors, basically both chemical sensors and biosensors, and energy harvesting in their solar cell and piezoelectric materials. In superconductor, what are superconductors? Anybody knows? I cannot interact with because there is a muted things. Okay, so I have to only talk from here. So superconductor materials which show zero resistance as well as diamatic in nature. Okay, so if the material which shows strongly diamatic signal as well as zero resistance, then that is called a superconductor, and it has a lot of applications. For example, in MRI, we can detect the tumors and cancer, whatever small magnetic field present in body, that also can be detected by using
Hello.
I think we have lost the range due to some technical reason. Sorry for the same.
टेक्निकल प्रॉब्लेम सर परत कनेक्ट व्हायला लागले असा विषय टाका पार्टिसिपंट चॅट मध्ये विषय टाका
चॅट
टेक्निकल प्रॉब्लेम्स Sirge sir is
shortly connecting.
Shortly connecting. Be patient.
Please stay with us.
Problems are available.
Connect shortly. Stay with us. Hello, Dr. Shirge.
Yes, can you hear me?
Yes, sir.
Have you joined? Yes.
Sir, proceed.
Thank you. Please proceed.
Just a minute. So slide still it's running or I have to share again?
Sir, please share again.
Okay, sir. Okay.
Okay. Okay. So I was talking about superconductor. We can use this superconductor for the transportation. For example, we can make a magnetically elevated train. We can fly it on the track and we can run with the speed of 500 km per hour. That is the speed of the aeroplane. And if we have to travel from Mumbai to Delhi, then it will take 2 hours. And we can use this magnetic elevated train and we can cover this distance from Delhi to Mumbai in just 2 hours. So that's another application. There are a lot of applications of a superconductor. Then magnetic nanoparticles, it has a lot of applications. For example, we can make a RAM, ROM by using this. Then I will talk about the batteries and supercapacitors. Supercapacitors, what is supercapacitor? Maybe few of you are knowing about these supercapacitors. Okay. So materials, some materials I will show how we can use these materials for making these supercapacitors. Then basically I'll talk about the sensors. They are very important. For example, biosensors or chemical sensors. Basically today I will talk about the only chemical sensor, not about the biosensors. Then energy harvesting, for example, solar cell, we need energy for long term now onwards, because whatever the sources, natural sources were there, they are consuming and no more natural sources are there. Okay, fossil fuels. Okay, so we have to use alternative ways, renewable energies like wind energy, solar energy, or all these things for future applications. So as I mentioned, superconductors. So superconductors, in earlier slide, I told about the high pressure synthesis technique. That is one of the important technique that can be used for making the new materials. So these are few materials which I discovered by using this high pressure synthesis techniques. These are completely new superconductors: calcium 3, aluminum 2, oxygen 5, iron 2, arsen 2. Basically, when we have a iron in the material, then that kills the superconductivity. But this superconductor has iron inside this one, and there's the very interesting things. Okay, so this is one. This is called 32522 superconductor. Then 42622 superconductor. This is also published in very reputed journals, Journal of American Chemical Society and Applied Physics letters. Then another important superconductor which I discovered is this barium 2, calcium, copper 2, oxygen 4, iron fluoride. It does not have any bismuth, thallium, mercury, but still it superconduct at 108 Kelvin. So this is the simplest non-toxic double layer superconductor and having the TC more than 108 K. Then I also discovered this calcium sodium iron to ascend to superconductor. Then ERFES hydroxide. Okay, both of these superconductors bear TC around 30 Kelvin. Okay. So another contribution which I made in this field of physics is that isotope effect. What is isotope effect? Isotope effect is nothing but when we vary the isotopic mass of the material in the superconductor, then basically TC will change. Higher the phonon frequency, higher will be the TC. If the material is having the, for example, I am giving the example of this iron, barium, potassium, iron to ascend to. If the material is having the isotopic mass 54, then it must show TC around 38 Kelvin. And if we change this isotopic mass from 54 to 57, then TC will decrease, because as the weight of these atoms will increase, phonon frequency will decrease, and as a result, TC will increase. But what I got the important and interesting result is that with increasing isotopic mass, TC is increasing. This is very interesting result that we got in this barium iron to ascend to superconductor, and this is published in Physical Review later. In 54 containing iron-based superconductor with this 1 to 2 system, TC was around 37.4 Kelvin. And when we replace 54 iron with 57 iron, TC increased to 37.8. So this is very large inverse isotope effect. This is the first report of reporting about the inverse isotope effect. Basically, whatever materials and whatever mechanism that is described earlier in the history, that is positive isotope effect, but this is negative isotope effect. That's why it's called as the inverse isotope effect. Okay. So in case of barium iron ascend 2. Another important contribution which I made is this 111. Earlier was 1 to 2 superconductor. This is 111 superconductor. Samarium iron arsenide and oxygen superconductor. Okay. And in this, what interesting result we found that if we change the isotopic mass, then there is no change in the TC. Okay. So basically, these studies are leading to the understanding the mechanism of superconductivity. Why they are superconductor? If they are superconductor, what is the mechanism? Electron-proton interaction or electron-spin interaction or spin-orbital interaction? All these information we can get from this one. That's why this is published now, also in Physical Review later. Okay. So these are earlier work. Now, what currently we are doing, that I will give you the information about that one. Okay. So outline of my talk will be like introduction of the material, why I'm using that material, then effect of the preparative parameters. Basically, I'm giving the information of zinc oxide. So how to prepare this zinc oxide in your lab? This is a very simple technique I will give you, and hope once you return back to your lab or when you go to your lab, then you can easily synthesize this material by using this technique. And how to utilize these materials for different applications. That's why I mentioned here multifunctional application of the zinc oxide nanostructures. Then I will summarize the talk. Okay. So I use the zinc oxide because this is a very interesting material, because this has a band gap of 3.3 electron volt, and this has very high melting point, and this is a very important parameter when we use this material for some applications. For example, for field emission, I'll give you an example about the field emission also. That time, this melting point is very important. Okay, so this has very high melting point, so this will be one of the best candidates for applications. Okay, then naturally this is n-type. Majority of the carriers are electrons, so this is act as a n-type semiconductor, and preparing zinc oxide with p-type semiconductor is very hard. It's very difficult, but that also have a lot of applications. But naturally, when we make zinc oxide, then that is naturally n-type semiconductor. Then this has very high electron mobility, more than 2000 centimeters square per volt second. Okay. Then not only this, I am giving only few examples why this is important. That is widely used for in electronics. For example, we can use for making the lasers, for making the leads, and transparent thin film coating of piezoelectric materials. Also, we can use this for the sensors, solar cell applications, also nanoscale gas sensing apparatus. or devices, and also we can use for the health care. Okay, for example, in medicinal purpose, we can use for cold rashes, antiseptic cream, sunscreen, lotions. When we have a UV rays, how to cut that? By using this zinc oxide, titanium oxide, that will cut the UV rays. If we interact these UV rays with our skin, then we can have the skin cancer. Okay, in order to avoid that, we have to use these some materials that can cut the UV rays, and that will not interact directly with our skin. Okay, so there are a lot of techniques. For example, chemical vapor deposition, where we have to use the tube, then we have to heat it at very high temperature, about 900 degrees centigrade to 1000 degrees centigrade, depending on the materials. Okay. Then physical vapor deposition, for this we need a laser or some other things in pulse laser deposition. Okay, very sophisticated instrumentation we needed. In atomic layer deposition also we need a very sophisticated instrumentation. Then electrochemical deposition technique, we need a electrochemical cells, then electricity, all these things, that is very complicated. Adjusting composition very difficult. So that's another drawback of this one. So basically I am concentrating on this wet chemical method, comparing to this all this, whether they need a very high temperature, high pressure, or some sophisticated instrumentation. But wet chemical synthesis technique, what we need is some beaker, then substrate on which we want to coat, then water, there is water and some salts. Okay, that's all. Then we'll get the very good materials. Then I'll give example about this zinc oxide. Okay, then which are the parameters which affect on this zinc oxide growth? Okay, so basically I'm considering 4 important parameters. In this I will discuss about that one. Okay, so when we start with the zinc oxide, we need a source of the zinc oxide, maybe zinc chloride, zinc sulfate, zinc nitrate, all these things. Okay, dissolve in the water, and once you dissolve in the water, then add that in the dissolved in water, then add some basic solution in that one. For example, KOH, NaOH, or ammonium hydroxide. Then that will start the nucleate. Then comes the parameters which we need to control. How much concentration we are taking? For example, 50 millimolar, 100 millimolar, or 200 millimolar. At which temperature? Once we prepare the solution, and at which temperature we are heating that material? Okay, that is important. Then how long we are preparing the material? Maybe 5 minutes, 10 minutes, 1 hour, 2 hours, 5 hours. Okay, that also make the very important information for the research. Okay, then another important parameter, what type of replacement is there, doping is there. Okay, depending on that, whether we are doping with the small NA or high NA compared to zinc, that also plays very important role in the preparation of the materials. Okay, so I will give one by one parameter controlling of this one. Okay, so basically I prepared zinc oxide nanostructure, I varied the concentration, then temperature, then time, and lastly I varied the doping. Okay, all these parameters I will show here, and at the last I will show the important information how to utilize these materials. Okay, so if we keep temperature around 100 degrees centigrade, we have 4 parameters. So I will only talk about the 3 parameters now. Doping is not concerned here. I'll come to doping that later. Okay, so we are keeping temperature around 100 degrees centigrade and time for 2 hours. Okay, then the parameter left is concentration. So we have to change the concentration. I utilized 50 millimolar, 100 millimolar, 150 millimolar, 200 millimolar, and 250 millimolar. Okay, and once we use this concentration, prepare the material, then scan is for using the scanning electron microscope that will provide the information about the surface morphology. And we can see that at 50 millimolar, it's a needle-like structure. And when we increase the concentration, that needle-like structure is forming the tapered needle-like structure, then converted into rod-like structure at higher concentration. Okay, it means that concentration is playing important role, and that is changing the morphology of the material of zinc oxide. Okay, by keeping 2 parameters, temperature and time constant. Okay, next what I will do that now I'll keep constant time 2 hours and concentration 100 millimolar. Okay, then I will vary the temperature, synthesis temperature 70 degree, 80 degree, 80 degree, 90 degree, 100 degree, 110 and 120 degree. Okay, with this also you can see that scanning electron microscope is providing very, very beautiful pictures of this one. Okay. So at 70 degrees centigrade, we are getting the needle-like structure. At 90 degrees centigrade, we are getting the 90 degree and 100 degree, we are getting the rod-like structure. And 120 degrees centigrade, we are getting the tube-like structure. It means that temperature play a very crucial role. And controlling temperature is very, very important when we prepare the materials. Okay. So change in morphology from needle, nanoneedle at 70 degree to 100 degree at rod-like structure, then at 120 degree a tube-like structure will be formed. Okay. Now, two parameters we already talked about. Now third parameter, okay, that is time. So in order to check this time, I have utilized two temperatures. One at 70 degrees centigrade, for example, A, B, C, D. These four images, I utilized temperature 70 degree, and remaining this E, F, G, H, these images, this sample prepared at 100 degrees centigrade. Okay. In this is also very clear that time play very crucial role, 30 minutes, 60 minutes, 90 minutes, 120 minutes. Okay. And with this, the rod-like morphology changing to tube-like morphology. Okay. This is also very important. It means three parameters we checked, and three parameters, all the parameters, they are playing very crucial role. So when we prepare the material, then it's very important to control concentration, time, and temperature of the synthesis very carefully, so that we can get the very good morphology, whatever desire of your material. Okay. Then I talked about the growth of the needles. Why that is forming the needle-like structure? That is also important. Mechanism behind that. Okay. What is the mechanism of growing of this needle or rod-like structure? So what we found that when we prepare the material, most of the material, they are oriented along 00L direction. They are oriented growing around 00L direction. Hope you are understanding this. 00L, the Miller indexes, okay, planes along which that material is growing. So this is growing around 001 direction. And when we prepare the rod-like morphology, then that is growing by using the layer by layer deposition. This rod-like structure is growing by layer deposition. That is what we found. And this needle-like structure, that is by screw dislocation. Okay. So screw dislocation. In between, something is coming on the screen, so that is disturbing my talk. Okay, this question, they are loading something. Please, can you stop this? Hello.
Hello. You may continue, sir.
But something is popping on this.
Yeah. We will collect the polling from the participants.
Okay. But something is coming on the screen.
Okay.
Okay. Thank you. Okay. So the mechanism behind this rod-like structure is because of the layer by layer, and needle-like structure is because of the screw dislocation. Okay. This is the mechanism. Okay. Then let's move to the next slide. Okay. Now, here comes the doping effect, the fourth parameter. Okay. When we replace zinc with some strontium or nickel, for example, zinc has an ionic radius of 0.74 angstrom, and when we replace zinc with this strontium, strontium has ionic radius 1.18, and automatically when we replace zinc with strontium, because of the higher ionic radius, the lattice parameter will increase. Okay. And in case of nickel has an ionic radius smaller than this zinc. Okay. Automatically, that constant will shrink. Okay. And that we can easily study by using this X-ray diffraction pattern. Okay. X-ray diffraction pattern will provide the important information whether your material is pure or not. Okay. And how to identify that pure or not? Basically, we measure the X-ray pattern, then compare with the standard JCPDS data, and your measured XRD pattern and standard JCPDS data, if they are both are matching with each other, then your material is pure. If extra peaks are appearing in that X-ray pattern, then you will be having the impurity peaks, impurity material in your material. Okay. And once we study this, first important information what we get from this X-ray diffraction is that phase purity. Then second is lattice constant. Lattice constant will provide the important information what is happening when we prepare the material. Okay, so that lattice constant, then strain, stress, bond length, all these can be evaluated by using this X-ray diffraction technique. Okay, so this is the basic tool when we prepare the material. That time we have to utilize. For example, look at this replacement of zinc with strontium. Okay, then this black line, black curve that is showing the pure zinc oxide, and with doping for 4% and 8%, the peak is shifting to lower theta. Okay, when we measure the 2 theta, then automatically it will provide the important information whether the lattice constant is decreasing or increasing. In this case, the lattice constant is increasing because the 2 theta is decreasing to smaller angle, and we have the black relation 2d sin theta is equal to n lambda. Okay, so automatically the shift of the 2 theta will indicate the change in the lattice constant. Okay, so in case of strontium, the lattice constant is increasing. It means that we are replacing zinc with strontium. Okay, in case of nickel, okay, this black line, black curve again, this is zinc oxide, and this red and blue lines curves, they are representing 5% replacement of zinc with nickel and 10%. Okay, this is unsystematic. First, this is decreasing, this is increasing. Why? It should decrease because no, we are replacing zinc with nickel. The ionic radius of the nickel is smaller than the zinc, but this is first decreasing, then increasing. This is not only the one parameter of only replacement of the material, but it also playing the important role that this is some modification is there, some other stress, strain, relaxation is also playing important role in it. That we can see. Okay, so in this, why the lattice constant is not continuously decreasing or increasing with this one? So for that, this is the important information that will provide. Pure zinc oxide rod-like structure. When you replace this with 7.5%, 10%, 12%, and 15%, then this is modified. These rods are modifying into plate-like structure. Okay, so that's why the stress-strain relation is changing. That's why the lattice constant is changing this one. Okay, unsystematically. Okay, now another important information. Once we prepare the material, then we should know the defect levels, and this photoluminescence will provide the important information. What type of defects are there, or whether defects are there or not, with doping, without doping, that information we can get. Okay, so we measured this photoluminescence by exciting at 350 wavelength. Okay, then 25 to 800 degrees centigrade. There are two regions, UV region and visible region. And if we take the ratio of this one, then normalize that green region, then the intensity at UV region is changing. For example, only this zinc oxide has the highest intensity, and replacement with strontium as well as with nickel, this UV intensity is decreasing. Okay, and if we take the ratio of this intensity of the UV to green, then that is decreasing with doping. That indicates that there are certain dopings that's changing the defect level in this material. Okay, so we have seen that there is change in the morphology, and now because of the doping, there is change in the defect levels in the materials. Okay, so in nickel doped zinc oxide, morphology changing as well as defect levels are changing. So we can easily pose the question, if the morphology changing or the defect levels are changing, is it possible to utilize this change in the morphology and defect level for useful applications? Okay. So for example, change in defects are very useful for the sensing and optical applications. Okay, change in morphology with enhanced surface area, that is useful for the charge storage applications, for example, for supercapacitor applications. So zinc oxide has a nanorods has a surface area of 4.35 meters square per gram, and if we replace this zinc oxide with nickel 12.5%, then surface area changing from 4.35 to 51.5 44 meters square per gram. Okay, so it means that because of doping, the surface area is changing. Rod-like morphosis is changing to flake-like structures. Okay, that is very useful for some useful applications like energy storage. So basically, now we control the parameters. We have the materials. Now we have to check this material for different applications. So I use this material for gas and humidity sensing applications. Okay, so I published two papers on this. Then for field emission, then understanding the basic mechanism. Okay, that is magnetic semiconductors. Then two photon observation. Then energy storage applications. So one by one I will give. So I utilize this nickel lobe zinc oxide for energy storage applications. For this we have measured this current voltage relation, that is cyclic photometry. And if we estimate the area under the cyclic photometry, then that will provide the information about how much charges we have stored in this material. And if we can utilize this formula, specific capacitance is given here. Okay, all this information, mass and scan rate and current voltage relation. Then we have estimated the specific capacitance, and by using the cyclic photometry, we are getting the specific capacitance about 625 Faraday per gram. Okay. Then another technique how to estimate this specific capacitance is charging discharging. Basically, we charge the battery and discharge the battery, and by using that cycle, we can estimate the specific capacitance of the material. Okay. So I utilize this discharging time to estimate the specific capacitance, and this also showing the specific capacitance more than 650 Faraday per gram. Okay, so our earlier cyclic photometry and charging discharging both are matching, and if you compare with the earlier reported data, then our material is showing very high specific capacitance, almost 3 to 4 times higher than the earlier reported, and it means that nickel lobe zinc oxide is very good for the supercapacitor capacitor applications. Okay, then another important application we tested for the device making. Okay, we have charged this supercapacitor for 10 seconds, and we lighten this LED. Okay, this will light for 2 or 3 seconds. Okay, but this is good material. Small prototype device we prepared in the lab. Okay, by using the polythene bag. Okay, you can also prepare in your lab. Then another important application of this zinc oxide is for gas detection. Okay, now you heard about the very high pollution in Delhi in November and December of every year. Okay, so there is disturbing something, the popping of something in between this one. That is really disturbing the thing. In between, something is joining, something is leaving. So it's very difficult to see the slides. Okay, so we have a lot of pollution in the environment. In order to detect that, we have to utilize this CO, CO2. These are the important greenhouse gases, and in order to detect this, it is very important to have the very sensitive sensor and selective sensor. Okay, so according to Occupational Safety and Health Administration, OSHA organization established the permissible exposure limit of CO about 50 part per million and CO2 of 5,000 part per million as 8 hours time average weighted average. Okay, if we handle more than this 50 part per million of CO or 5,000 part per million of CO2, then that is not good for the health. Okay, that will seriously damage our nervous system or some other parts of the body, and that will produce cancer or tumors in the body. So it's very important to detect these toxic gases. So for these metal oxides, for example, zinc oxide, have very advantageous property because they are highly sensitive and they lead very low power consumption and low price, because zinc oxide is abundant in the nature. Okay, and they will give the quick response time when we expose with these toxic gases, then that will give the response in few seconds. Okay, so that's important information. Okay, so in order to measure this sensing property, either we have to measure the capacitance or resistance. Okay, For example, I utilize this to measurement. Okay, I measure the resistance of the sensor with different concentration of the exposure of the CO, and with increasing the concentration of the exposure of the CO, this resistance is decreasing. It means that sensor is working, and that is giving the very good response and recovery time. The response time is about 10 seconds, and recovery time is about 15 seconds. Okay, and if we can measure the calibration curve of this one, that calibration curve is nothing but the change in the resistance with change the concentration of this one when we expose the different amount of concentration of the CO. Okay, and by using this sensor, we can detect the minimum 2 parts per million. It is very small amount of CO present in the atmosphere that we can easily detect by using this one. Okay. So if we use this nickel dope zinc oxide, then we can make a very good CO sensor. Okay, and that is I'm showing only highlighted part. There's selectivity and other things. I am not talking about that one. Okay, then if we dope zinc oxide with strontium, then this will be good CO2 sensor. And by using this, again I measure the resistance, and with the different concentration of the CO2, the calibration curve we plotted, and that by using this calibration curve, the minimum amount of CO2 we can detect is that 0.25% of the CO2 present in the atmosphere by using this one. Okay, so it means that nickel doped zinc oxide is good for CO sensor, and strontium doped zinc oxide is good for SR sensor. Okay, and what is the mechanism? Why it's changing? Basically, what we thought that CO is absorbing O2 minus and producing CO2 plus 2 electrons, that is providing the change in the resistance. And this is a possible mechanism we propose for this working of the sensors. And we did compared with the earlier literature, nickel doped zinc oxide. Then this is showing very good response time, and this is operating at very low temperature compared to earlier literature. Our sensor is working at 250 degrees centigrade, and the sensor which works at room temperature is very good, but working sensor at room temperature is very difficult. So we have to use some temperature. So we prepared this, we measure this sensing property at 250 degrees centigrade, but compared to earlier literature, our temperature is very less. Okay, 250 degrees centigrade, and response is 2.5. That's compared to earlier, this very good response. Okay. Also, we prepared this humidity sensing. Humidity sensing is one of the important when we use some agricultural product or industrial applications. Then there's another important thing. Then ammonia is another toxic gases. We need to measure this ammonia. So for that, nickel cobalt hydroxide we have utilized for detecting this, for sensing this ammonia, and we got the very good result in this one. I'm not going into details. So coming to only zinc oxide, field enhancement. Okay. Field emission is very important property. For this, I utilize nickel doped zinc oxide for the field emission properties. Field emitters are important potential applications because these field emitters can be utilized for the display, flat displays. For example, TVs and large screens. For that, we need these field emitters. Also, in transmission electron microscopy or scanning electron microscopy, we need a source of the electrons. For that, we need a generator of the electrons. For that, we can utilize. For generation of X-rays, again, you can utilize this one. So in this case, zinc oxide is promising material for field emitter because it's high thermal and stability. I already mentioned that the melting point of zinc oxide is more than 1900 degrees centigrade. So this is very good thermal stable. Then it's the resistance to oxidation, because if we change the humidity or something, its property will not change. It will be the same. Okay, that's why it's very good for the application. So how we measure this field emitter? We apply the field, then we measure the developed current. Okay, basically charges. Okay, so there are two definitions: turn on field and threshold field. In order to generate 1 microampere per centimeter current, that is called as the turn on field. And when it reaches 10 microampere per centimeter square of this current, that's called the threshold field. In case of zinc oxide, this threshold and turn on and threshold field are 2.5 volt per micrometer and 2.8 volt per micrometer for the zinc oxide. Okay. In case of 10% nickel dope zinc oxide, this turn on field and threshold field, they become lower. It means that we need a very low energy to get this turn on field and threshold field. This is 1.8 and 2 microvolt. Okay. So this is very good. Nickel dope zinc oxide is very good for field emitters. Another important information what we measured is the 2-photon absorption spectroscopy of this material, nickel dope zinc oxide. And what we found that we measured the absorption, this Zeta scan, basically transmission of that light from that material and how much it will transmit. That will give the important information about the coefficient of the absorption coefficient of that particular material. Okay. In case of pure zinc oxide, this beta is 7.6, and when we replace this zinc with nickel 10%, then it's 112. Beta is 112. It means 14% increase in the beta, and that is very good for the lasing applications. Okay. Okay. So this nickel dope zinc oxide is very good for lasing applications. So another important material what we studied is graphene. Reduced graphene oxide we coated with the silver, and we found that this is very good for the antifungal activity. When we interact with this reduced graphene oxide with silver particle, then that kills the fungus, and that's good for antifungal applications. Okay, this is not related to zinc oxide. Just I wanted to show. Okay. So in summary, controlled growth of zinc oxide nanostructure is demonstrated successfully. The growth mechanism is explained, and zinc oxide nanostructure application is supercapacitor, gas sensor, 2-photon absorption, and field emitter are successfully demonstrated. I'm very sorry that in between something was popping up that was disturbing my talk. So this is end of my talk. If you have any question, then I will be very happy to answer that questions. Hello.
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 Yes.
Paras madam. Hello, Paras madam.
Yes, sir. Yes, sir. Yes, participants can ask the questions personally to the resource person. I could see certain raised hands on the chat box.
Please, can you read one by one so I can answer?
Sir, please unmute somebody who has raised the hand. एक raised hand ला you can unmute him. Okay, fine.
Water parameters.
Sir, there is one question from Dr. Jeevan.
Yes.
What parameters are studied to estimate the inhibitive action of these materials?
Inhibitive act. What really you want to know?
What parameters are studied to estimate the inhibitive action of these materials, sir?
Which material?
Actually, Dr. Divan Mohindru, he has given this question, asked this question, particular question. Dr. Jeevan Mohindru, sir, if you can unmute him, we can have the dialogue with sir. Yes. Let's proceed toward the second question, sir. By that time, sir, what other dopants that we can use to enhance the property of ZNO? Zinc oxide. Sir, can I repeat the question? What dopants that we can use to enhance the property of zinc oxide?
रेज हँड आलेत बघा अस्तबोईल सर रेज हँड आलेत पहा अस्तबोईल आहे त्यांना
Hello Shirge sir, I think there is some technical issue. Shirge sir has lost the connectivity. I request the participants to ask the questions if they have any. A few participants have raised the hands. I could see on the screen.
Okay, we begin the third technical session and now.
Okay.
After we will take questions.
At the end of the third session, if possible, we will invite the questions. Let's move towards the last technical session of this webinar. We are honored with the graceful presence of the resource person, Dr. R.S. Devan, Associate Professor, Discipline of Metallurgy, Engineering and Materials Science, Indian Institute of Technology, IIT Indore. I would like to request Mr. S.A. Shinde, Assistant Professor in Chemistry, to introduce the resource person. Over to you, sir.
Hello, I am Sriram Shinde, Assistant Professor in Chemistry, is pleased to introduce today's resource person, Dr. Rupesh S. Devan, sir. Dr. Rupesh S. Devan is working as Associate Professor in the discipline Metallurgy, Engineering and Material Science, Indian Institute of Technology, Indore, India. He completed his MSc and PhD from Shivaji University, Kolhapur, and postdoctoral degree at National Hong Hoa University, Taiwan. Now we're moving towards the honors and award received by Dr. Devan. He is awarded with Duo India Professor Fellowship Award, ACM Duo, South Korea in January 2020. He is the editor of Chinese Journal of Physics, January 2018. He is awarded with the professional member, International Solar Energy Society, October 2019. He is awarded with Inspire Faculty Award 2013 by Department of Science and Technology, DST India. He is awarded with the Excellent Grade 2017 for Inspire Research Project by DST India. He has been a postdoctoral fellow in between August 2007 to December 2013, Ministry of Science and Technology, Taiwan. He is Young Associate from 2015 of Maharashtra Academy of Science. He is awarded with the Excellence in PhD Research from Shivaji University, Kolhapur, India. He is Associate Member, Institute of Physics, London, UK. Now moving towards the academic activities, he is an editor of Chinese Journal of Physics. He has written book on applications of one-dimensional nanomaterials, ASP USA 2019. He is a lead guest editor, special issue, functional nanomaterials for energy applications of Journal of Nanomaterials, Hindavi Publishers. He is editorial board member, American Journal of Material Science and Engineering, Science and Education Publishing. Now moving towards the publications. In his research field, he has published 1 book, 2 book chapters, and 97 research articles in SIC journals. He has a citation more than 3956. H index is 38 and I-10 index is 70. considering the research guidance, number of PhD students, ongoing 8 students, and 4 students completed MPhil under his guidance, and master students, 5 students are doing project, and 7 are completed. Thank you.
Thank you very much, Mr. S. Shinde sir. May I request Dr. R.S. Diwan sir to make his presentation?
Yeah, thank you very much.
Over to
Am
you,
I
sir.
audible?
Yes, sir. Please proceed, sir.
Yeah, thank you.
Yes, sir.
Since morning, everyone is busy on this webinar. And at the end, I'm going to talk about nano-heteroarchitectures as a state-of-art technologies. So since morning, you have heard about Raman, then few nanotech materials. But I'm going to talk about the combination of different nanomaterials. So that's why I give talk title as a nano-heteroarchitectures. So why nano-heteroarchitectures are more important? If you look at this picture, then few of us might be knowing that our revolution start visibility in 1913 to 1956, where black box TV was there with having one shutter, and then slowly it converted into a color TV, which was very expensive. Then we will start talking about the computer, and then slowly cell phone enter through the Nokia in the market. And then after that, the size of the cell phone goes on varying. Then a big pager converted into a very small and very handy cell phone. And after that, we start talking about flexible display. So many companies start discussing about flexible display. And now we are talking about the correlation of different displays. So why does it happen? Definitely something is playing a role at the back end, because if any device is reducing its size day by day, that means really components are being tailored, and that's happened because of the nanotechnology. But does it only nanotechnology? So of course not.
Okay, sir.
So am I audible? Hello?
Yes, sir. Yes, sir. Yes, sir. Proceed.
Okay, so in between, please don't change, because I observe that someone mute me again. So please, okay. Yeah, so a revolutionary industrial revolution starts with textile in end of 90s, and early 90s railroad come in a picture. So it was correlated with automobile and then computer. So automobile is correlated.
Excuse me, sir. Adjust your cameras, please.
So camera is not important. I think voice is more important.
Okay. Okay, sir. Okay, fine.
Okay, so computer come in picture. So if you look at the development, it was before 70 that this computer was at introductory phase, and then widespread adoption started. So still we are adopting this computer technology. So artificial intelligence may be the end of this computer technology, and then with this artificial intelligence, that nanotechnology may come in picture. So right now we are just introducing this nanotechnology to the world, and widespread adaptation, that means real applications may start in a couple of years, and that will go on till end of this century. So we are on the age of nanotechnology. So artificial intelligence may be the start of it. So if you look at all these scenarios, then the question comes out where our industry is focusing. So if you look at industrial focus in particular nanotechnology, then it starts with hybrid materials, then information technology, semiconductor 70%, then nanomens 11%, medical and healthcare is total, with other contributing for 18%. So what more focus given is hybrid materials. So that means nano heteroarchitectures are going to play a major role in this development of technology. So all these nanostructures are divided into 4 major categories, which start with 0, 1, 2, and 3Ds. So 3Ds nowadays are called as a hierarchical structures. I'm not going to talk about these definitions, but what these structures involve is the pristine structure in their original format, or you can go with decorating. You can see here this decoration has been taken place, or you can form a composite, or you can mix it together. But if you look at the development, 3D nanostructures were developed first because of the bulk materials were available in the market, and then 3D materials converted into a 2D format in the form of thin film, and then people start talking about the quantum dots, because zero-dimensional structures play a major role in the technology. So what was lacking behind was one-dimensional structure. So relative to other three, the development in one-dimensional structure happened a little bit less, later stage. So why zero-dimensional structures are more important? Because zero-dimensional structures are known to be a quantum dot. Theoretically, it has been proved that they can tailor a lot of applications and they can play a major role in tailoring the properties. But does it really happen? If you look at this picture, then you will realize that it's really happening. These zero-dimensional nanostructures are really creating a lot of excitement, because broad absorption, narrow emission, single excitation of the source is possible with these zero-dimensional structures. So if you look at this particular place, then this mouse is carrying 3 different quantum dots, and based on this excitation, you can change the color. So this created a revolution in the medical field. That means you can carry these particles, nanoparticles, attached with drug and place in a cancer cell and just cure the cancer cells. So this selectively taking place in a cancer field. So these zero-dimensional structures created excitation. But is it happening only with the medical field? Of course not. It's happening with other fields as well. So if you look at the optical storage, the gold nanoparticles can be a very good example, because gold is a color. That's what we consider. But if you change the particle size into a few nanometer differences, then you can change from gold to red, and there are different colors as well. Apart from that, nowadays people are talking about quantum dot LEDs, where you can really tune the color from blue, red, or any other color. Then organic dyes nowadays are coming in picture because of organic dye sensitized solar cells are also there. These people are using organic dyes to tailor the properties. Then quantum computing. So this is the best example. You can see these are the electrodes connected with the quantum dot, and you can really tailor the electron passing through these quantum dots, and you can control the electric circuit that's happening actually. The security is another example. So you can put your particles over there, and then you can excite them using the optical, using the particular wavelength, and you can check out, does it really happening, or does it really belongs to you? Nowadays, people are using holograms, but compared to holograms, if you consider optical storage and the emission, then this security can be maintained very nicely. Then next comes with the solar cell, solar power. So quantum silicon being used. But what excites more is the heterostructures of this quantum dot. So if you look at this picture, these are the particles of this titanium, and then comes out with the particle of the CDSE. So these are close compact, even though surface area is larger. So the path traveled by this electron was taking a longer distance. But if you compare the tubes, which are over here, the tubes having a larger surface area compared to particles, and then they have been attached with the quantum dot. So this created a lot of excitation, and then this improved the efficiency of the solar cell as well. But after that, what people did, they created this CDSE quantum dots with different particle size, which moves from 2 to 4 nanometer, and they put in a rainbow cell. So what happened here is 4 nanometer particles were at the bottom, and then they start decreasing the particle size, and they start coating different particles up to the top. So that really helped for the absorption of a large number of reflected lights, and that's created a very good efficiency out of the solar cell. And nowadays, if you look at this, there was a big news in advanced science that the MIT researchers break the quantum dot solar cell efficiency record of 9%, and they reached to the 20 to 30%, and they are thinking about 65%. This happened in 2014. So far, we have not reached the 65%, but we are close to 40% approximately. So the day is not long to reach 65% with the quantum dots or nanohetero architectures with these solar cells. But does it happen that only zero-dimensional structures helping to improve the applicability? Of course not. There are other two materials which are 0 and 1 and 2 dimensional materials which are competing with these zero-dimensional structures. So there is one story with future minute miles which can be correlated with this 1D and 2D nanomaterials. So before 1950s, it was thought for many years that human body is incapable of running a mile in 4 minutes. That was true. But in 1954, Roger Binster from Oxford University broke the record, and he just crossed the distance less 1 second for the 4 minutes, right? But what happened after that, in 2 months' time, this John Landy from Australia did it again, and he took just 3.58 minutes, which was very short. So this thought was broken by these two guys, and now it's become a commonplace. If you look at the Hussein Bolt, who placed a world record in 2009, he ran 200 meters distance in 9.58 seconds. So if you ask him to continuously run, he may break these 3.58 minutes into 2.3 to 2.5 minutes. Then same way, this Van Vanny, who placed a record in 2016, which is recently for 400 meters with 43 seconds. He may run this distance in a 2.58. So they are race mats. So what was thought before 1950s become a commonplace now. So same thing happened with these materials as well. So there was a thought for many years based on thermodynamics that it is impossible for the single atomic layer to be exist independently. And Professor Izima in 1991 showed that that carbon plaques can be wind together, maybe one layer to maybe two layer or up to 10 layers, and can form a carbon nanotube. So he gave a very nice introduction about the folding of these carbon plates to convert into nanotubes. So, but what happened here? He couldn't succeed to create a single layer carbon nanotube. So he couldn't achieve his wish, might be of might be of a Nobel Prize. But after a few years, in 2004, Andre and Professor Constantine from University of Manchester, they created a history by exploiting the single layer of graphene. So they published their paper, submitted their paper in Nature, which was a 3-page paper, which was rejected twice. The first time it was said that isolating a stable and two-dimensional material is impossible. Of course, thermodynamics says that before their research, right? And then another comment was for a second time that this is not sufficient scientific advance. Just imagine the reviewer giving these two comments and rejecting the paper on the graphene. Then they published this paper in 2014 October in Science with the title Electric Field Effect in Atomically Thin Carbon Film. They not say it as a graphene, they said atomically thin carbon film. And then they received a Nobel Prize in 2010. And that time, the two-dimensional materials become hot. But you just imagine this two-dimensional materials, if you fold it to convert into one-dimensional material, then you can tailor the properties. So combination of one-dimensional and two-dimensional material can be hottest topic for the research. So what are these one-dimensional materials? So they are always confined in two directions and move the electrons in one direction along their length. So I'm not going into the definition. So these are the nanostructures, one-dimensional nanostructures you can observe in the literature. Few of them are from our lab. So what people are doing, they're putting some quantum dots or some extra particles, or you can say foreign particles, and they're creating some hierarchical structures of this one-dimensional structure. They are tailoring this depicts inside so that you can change the growth direction and you can form the helical-like structure, or sometimes you can form the comb-like structure. Zigzags are also there. These are all tailored with the controlling defects. And you can even create some air voids inside the structure, and you can create a barcode nanowires. The bullets are there. So there are a lot of one-dimensional nanostructures available in the literature. And these all nanostructures are grown with some different strategies. There are total 6 strategies known till 2001. So first is anisotropic crystallographic growth of solid materials, and then happens to be a liquid solid interface at 1 inch so that it can grow in along one direction. Or you can use various templates, one-dimensional templates to create another materials. And then two-dimensional materials can be reduced in one direction so that it can be converted into a one-dimensional structure. Or you can continuously connect these carbon quantum dots to convert into one-dimensional structure. Or you can go with capping reagents. So you can put capping reagents along these two sides and then let this structure go along the one direction. So these were the growth strategies known till 2001. But the growth strategies is not really a growth mechanism. So these all growth strategies belongs to a certain growth mechanism. The first one is VLS growth mechanism, where you have to use vapor, which can come in contact with catalytic particle, which can convert into etiolatic liquid droplet. Then these vapors can convert into a liquid format and form a etiolatic liquid droplet over here and let the solid phase growth behind. So This vapor converted into a liquid and then converted into a solid format. This is as simple as it looks. But what excited more, that this liquid droplet always carries this foreign particles as an impurity inside the structure. So we have to remove this liquid particle. So people start thinking on this, and then they converted the vapor directly into a solid. So this is the vapor solid growth mechanism, where you can directly heat the metal and convert into vapor format. Then this vapor can come in contact with your oxygen if you want to go for oxide layers, and then you can form a stable oxide phase in a vapor format. Then rather than converting into a droplets, you can directly convert these droplets to nanomaterials, what was happening in VLS growth mechanism. You can stop conversion of these droplets from vapor, and then you can directly move to the one-dimensional growth. So here you can avoid the capturing of the foreign particles inside this structure. And there is other method where you can go with close reaction, which is called as a solution liquid solid growth mechanism, where you can have organometallic precursors with catalytic particles. So this organometallic precursor will reach to the supersaturation state after nucleation, and then that will let this solid growth behind. And during this supersaturation state, byproduct will come out. But this byproduct will always remain inside this closed compact reaction chamber. So there it may happen that these byproducts can get intercalated with this structure. So if you want pure structures, pure materials, then you can go with vapor solid growth mechanism. Apart from that, these two-dimensional materials, which are confined in one direction particularly, the best example for two-dimensional materials is a graphene. So how to grow a large size graphene? So you can say this is the best method known as a chemical vapor deposition. And the Samsung company has created a display with 3-inch size made up of graphene. And they have done now this with flexible touch screen as well. So the question comes out, if you want to create such kind of big displays, then how much graphene is required? So let's consider the P to understand, because you can calculate the length and diameter, and then you can easily understand how much area of this pane is there, and based on that you can decide how much graphene is required. Let's consider it's a couple of micrograms. Then let's consider next bigger size is coin. So if you move from pin to coin, maybe 10 pins required to complete this one coin. So maybe 10 micron, couple of 10 microns. Then think about the cell phone. Maybe 10 more coins can cover this cell phone. So 10 times is increased. Then consider about laptop. This cell phone, 10 or 15 cell phones required to cover this whole laptop. So again, it's increased. Then think about the dog, which is a little bit larger in size compared to laptop. So let's consider 5 times larger. Then it comes to the car. So definitely it's 20 to 15 times larger. So up to this, we can think of maybe it's required 1 kg of the graphene to cover this car. But what about elephant? Even it is bigger than size. So maybe 10 kg. But people are thinking about covering this Empire State Building, which is the first highest building across the globe. So they're thinking about how if we cover this building with the graphene and convert into a touchscreen, then how much it's required. So if element is taking about the 10 kg, then you can think about it's really, really higher, but it's not going to happen because we have to consider the first thing, the graphene ring. So you can think about how we can convert into this area. So if you look at the periodicity, then 2 atoms, graphene atoms are there in a periodicity form. So if you start calculating actual weight required, then you have to consider first hexagon of this graphene. Then you can calculate how many atoms are present there. Then you can calculate the actual area of the hexagon, which comes to be 0.05 nanometers square. Then you have to calculate the area for Empire State Building. You have to consider the height, which is 381 meter, length is around approximately 130 meter, and the width. If you calculate area for this, it comes to be 1.5 into 10 raised to 5 meters square, which is quite larger compared to this graphene hexagon, which is approximately 0.05 nanometers square. So how many carbon atoms are required? If you look at these, then we require total 6 into 10 raised to 24 carbon atoms. So if you convert into a nano format, then approximately you can consider carbon atom with 6 protons, 6 neutron. Then total 12 grams of 12 grams of graphene comes out for 6 into 10 raised to 23. So if you calculate actual amount of graphene required to cover this Empire State Building, it's just 120 gram, which is very, very less. So this can be a major runner-up in future technology. But is only graphene available in the 2D form? Of course not. There are other materials as well. So these are the graphene families. There are two-dimensional chalcogenides and two-dimensional oxides as well. But are they all stable? Of course not. If you look at this color, then they are stable at ambient atmosphere. That means you can use for any kind of application. You're not required to have a vacuum once you synthesize them. But if you look at this color, they're probably stable in here, but not much data available, because what happened, if you look at this particular oxide, they can reach to unstable state. So people are thinking that they may be stable at ambient atmosphere. But if you look at these, they are three-dimensional compounds, but not much later is available on this, because if you look at example of titanium dioxide, they are always grown in the form of quantum dots or one-dimensional structure. Very rarely they are observed in two-dimensional forms. So people are trying to create two-dimensional structures for all these materials. So not much information is available about this material. So they are known to the world, known to the scientific community, or as well as industrial community, but they are unstable at air, but stable at inert atmosphere. So if you want to tailor them in a vacuum, then these are the best materials to use for a variety of applications. But are these all materials have been exciting to the scientific community? Of course not. But what exciting more, if you look at the range, what these two-dimensional materials are covering, they are covering from visible to radio waves. But out of these all materials, nowadays people are focusing on this MOS2 if you want to go for optical or electrical applications, because the band gap lies between 1 to 2.5 eV, which can compete with germanium and silicon as well if you tailor a particular property. So this material is going to run the show in future. But is it happen that only single material is useful? Of course not. If you look at this lasagna, which is one of the best or tastiest food across the globe, it tells us many things. If you look at this upper layer, this is two-dimensional. If you look at this, there are quantum dots lying. In between, there is something which can tailor the properties of this two material. So if you put this two-dimensional material, then one-dimensional or quantum dots. So if you put one by other, then this can be a very tasty food. What if we do same thing with this one-dimensional, two-dimensional, and zero-dimensional material? Of course, before that, we have to think about two-dimensional materials. We are putting it atomic lasagna. That means different materials are stacked one above the other. So each material having different properties, different band gap, and they have different optical properties. So if you tailor them together and if you sandwich in particular manner, they can give you a very good application out of it. So people are thinking about putting this atomic lasagna together, but it is not that easy task. So we'll see how the 0, 1, 2-dimensional materials are useful as we are thinking about nano heteroarchitectures. So we will think about some synthesis part, then how to characterize them, and few of the applications. Basically, I will be talking about millimeters. So first we'll see this 2-dimensional, 1-dimensional nano heteroarchitecture. So titanium dioxide is known to be a very good material for electrochromic smart windows, and it has shown very good properties for supercapacitor, which can shows the cyclic stability up to 10,000 cycles. There are very less materials which are showing the cyclic stability up to 10,000 materials for a supercapacitor. So this excited us. What if we put these two one-dimensional material for the field emission displays? So why field emission displays are important? If you look at this particular picture, they're having a very good color combination. This field emission display is created by Sony TV, which gives a very good picture quality. And nowadays people are thinking about creating lamps using this field emission displays, and which is having very simple combination and which can be associated with PSM as well. So the thought was that this PU8EL, what they tell, that TiO2 and MOS2 can be clubbed together, but their thinking was different. They use this buckyball kind of things. Actually, this is not a buckyball. They created a spherical nanorods, and then they try to cover this MOS2 with two-dimensional structure. So their idea was to cover one-dimensional and two-dimensional structure together, but it did not happen because when they use MOS2 as a template, then they couldn't create these one-dimensional nanorods of the TiO2, but they created the particles over it. So they consider two heterostructures. One is MOS2 covered by TiO2 and TiO2 covered by MOS2. But their idea was to cover single nanorod. That not happened, but they covered whole nanorod structure. So nanorod become inside the structure, that means shell, and this two-dimensional structure as a core and cell structure kind of things. So it looks like to be here, but they couldn't cover it properly. So that was lying like an island on these nanorods. So if you look at the properties, they achieved turn-on field quite higher. It was approximately 4 volt per micrometer, and the stability was not that good. So we thought, let's take this challenge, but we thought not to go with rotary structure, go with the brookite structure. Brookite is a metastable phase, which is quite difficult to synthesize, but we have done it in our laboratory. So you can see these rods are vertically aligned, and all are lying in between 5 to 20 nanometer, but most of the rods are lying with the diameter around 10 nanometer. And then we confirm this brookite structure using TM and XRD. So after that, the challenge was how to put this MOS2. So we decided to go with a thin layer of 4 nanometer of the MOS2 over TiO2 so that these one-dimensional structures remain intact. And then we slowly go on increasing the thickness of this MOS2 over it. So it reached to 20 and 40 nanometer. And then we confirm how much layer is forming. So we can see here in the cross-sectional view that MOS2 is covered on TiO2. So this become a quite compact. If you look at the earlier images, these nanorods were quite opaque. They were individual, independent nanorods. But once you coat the MOS2, then they become a little bit compact, and thickness was increasing with the change in parameter during this deposition. The next challenge was, does it happen that TiO2 remain intact? That means no suboxide phase form. So we check it with the XPS. So XPS shows that initially the TiO2 remains in its proper format, 1:2. But when you form this 4 nanometer layer or 20 nanometer layer, then TiO2 may change, or MOS2 may change its own properties. Then MOS2 may convert into MO oxide as well. The biggest challenge was how to identify that 4 nanometer layer happened to be on TiO2. So we check with XPS, because XPS gives an information of few nanometers, that's 10 nanometer. So if you're considering 10 nanometer, that means upper layer of 4 nanometer should be MOS2, and bottom, the 6 nanometer should be TiO2. So you should get signal from both MOS2 and TiO2, and that's what happened here. So when we were having 4 nanometer MOS2 layer on TiO2 signal comes out, and that gives an information that TiO2 remain in its original form 1:2. But once we move for 4 nanometer, the TiO2 was not happen to be there, and we lost the TiO2 signal. The question comes out that TiO2 having the oxygen layer over there, then when you put MOS2 on it, then MO get oxidized, but we have not observed any oxidation signal over here. So that indicates that whatever we are talking, that MOS2 being synthesized as it is, it's true. At the same time, MOS2 signal decreased for 4 nanometer layer because the amount of MOS2 was there on the 4 nanometer. So when you move for 20 nanometer, signal increase. So this indicates that really we are talking what we are talking is a true. That means we are having 4 nanometer, 20 nanometer, and 40 nanometer layer of MOS2. So when we check these field emission properties, then what we observe on TiO2, proper TiO2, we could get turn-on field only up to 3.9, but when we coat 4 nanometer or 40 nanometer layer, it's reduced up to 2.5. That means really nano heteroarchitecture formation helps to improve the properties. Then we thought, rather than going for 2-dimensional structures, let's go for quantum dot, because in field emission, we have to have more emission sites. Because earlier state, what we are talking about, this 1-dimensional structure can cover with 2-dimensional structure. That means 2-dimensional structures will convert into 1-dimensional form, actually, even though they form a nano heteroarchitectures. Then we decided, rather than covering it, just put quantum dots on it. So each and every quantum dot can act as a emission site. Okay, so that's what we did. So first we synthesized this zinc oxide nanorods in a 1-dimensional format, which is having T format, and then we cover it with the gold nanoparticles. So different reaction parameters were obtained. And then we confirm really gold is lying on these 1-dimensional forms. So you can see here very nicely, these gold nanoparticles are being coated across these 1-dimensional nanorods, and this diameter of this nanoparticles was less than 30 nanometer, and we have confirmed with this TEM as well. The most important challenge, once you put this gold nanoparticle, does it tailor the properties of this zinc oxide? So first we check whether we have formed pure zinc oxide phase, then using XPS we confirm it. That what we observe, once you start coating the gold nanoparticles, but what we have done is we have changed the reaction time from 2 hours to 48 hours. And what we are observing that as soon as you move with more reaction time, number of gold particles are increasing. So that's what we have observed even in XPS. As soon as you increase the reaction time for 8 hours, your gold concentration increases. For 24, it's again become more. Now the question is, even though these particles are approximately 20 to 30 nanometer, and XPS says that the signal comes out only for 10 nanometer, then how come we are getting signal from zinc? We have to remember that these particles are being floated or being coated on the surface, and these are not continuous. So you can see over here, these are just randomly aligned. So for XPS, both the signals are accessible. That's why we could get this information out. And you can see here, as soon as we increase the reaction time, gold quantity is increasing and it's reached to the supersaturation state, or you can say the saturation state after 24 hours. And even if you increase the reaction time, these gold nanoparticles were agglomerating. So we can see the information about this decarbonylation. This gold nanoparticles have been observed here within pure form, and the zinc oxide is there. So when we check the field emission for this zinc oxide, then the lowest turn-on field was 1.31. But as soon as you go on increasing the gold concentration, then you can change the turn-on field from 1.31 to 0.96, which is really less. What happens over here? So you can see the stability remains almost constant compared to earlier report. It is far better. What happened after coating the gold? These electrons in a zinc, which were moving to the conduction band, were provided an emission. Here, because of this gold, they were accumulated together, and this was supported by zinc. So more number of electrons were provided by zinc and gold together. That's why we could get better results out of it. Then we check the water splitting. So you can see as soon as you increase the gold concentration, that's current density is increasing, and the same thing happening over here. Then we thought, why not to change the morphology from 1D to 2D? Because nowadays people are concentrating more on 2D. As I mentioned, that atomic lasagna is helping us to improve the property. So we move from thin film, convert into belt convert into a nanoflex, and we check out these nanoflex were in a porous nature. You can see these nanoflex or nanobelts were porous in nature. And then we check out when we change the morphology, does really happen that NiO remains intact, or it is in a suboxide form. So if you look at this 2D format of XPS, then this spectra remains constant even though you change the morphology. That means when you change the morphology, your atomic arrangement, or you can say the chemical composition not change. It remains to be NiS2O, it remains 1S21. So when we check the supercapacitance, what we observe is one-dimensional perforated structure gives very good specific capacitance, used to be close to 800. But what surprised us is this two-dimensional structure couldn't give us a better supercapacitance value. One reason might be this one-dimensional structure goes completely vertical, so loading was more, and here in two-dimensional structure, it happens to be flat, so loading was less. So that might be the reason. But if you look at the energy density, it was quite higher. It's reached to 55 watt-hour per kg, and the stability was really good, even if you check GCD or CV. So if you look at the future perspective of these nano heteroarchitectures, even though you are converting from one format to other format, or you are covering one format with other format, then that can be useful for energy storage and photocatalysis. So our group is concentrating on supercapacitor application. And nowadays we are talking about the photocatalysis. So we are looking for the hydrogen evolution and as well as dye degradation. So this is my group. We have right now 9 PhD students in our group, which are engine of my lab actually. So without them, I cannot do anything. Then we have 1 intern research scholar, 5 master student, 3 bachelor, they are going to pass now, and 1 visiting fellow. So these are our international collaborations, and these are my funding agency. That's it from my side. Thank you. And this lecture is open for discussion.
Excuse me, sir. Devan sir.
Hello.
Yeah, please. Yeah, please.
Devan sir, there is one question.
Yes.
Hello.
Yeah, please tell me.
There is a question from Ketan Kumar Gaikwad from Somaya College, Mumbai. He is asking, it is possible to tailor 2D heterostructures for flexible, transparent, and high-density memory storage applications.
Yeah, it's possible. You can see in my first slide, when I was showing two-dimensional structure, I have shown you Samsung photograph. So they have created it.
Okay,
Yeah.
sir. Okay. And one more question is there. He's Prem Kumar K. He's asking that how can you remove reduce the graphene oxide?
Okay. Reduce graphene oxide. So the question is a little bit tedious. How to remove reduced graphene oxide? Do you want to say that how to prepare reduced graphene oxide, or you can say how to remove the oxide from the graphene oxide?
Maybe like that.
So,
Maybe he
so
want to
there are
ask you
different,
that remove oxide
there are
from.
different aspects. Actually, this chemical vapor deposition is being used to remove the oxygen from the graphene oxide. I'm not expert in that field because I have not done work on graphene oxide. So sorry, I cannot talk in detail.
Okay, sir. Okay, no problem.
Yeah. Is there any other question? Let me check.
One more question is there, sir, from Amlan Rajan Rising. He asked that what about nano fertilizers, and is there any institute in India which is working on it?
Nano fertilizers.
Yeah.
See, the concept of fertilizers is different.
Yes,
if you're
sir.
talking about nano fertilizers, then it's really tough to talk on, right?
Yes.
So I have not come across any such company which is talking about nano fertilizers.
Okay, sir. No problem. Yeah. Okay. No more questions are there, sir. Okay, thank you, sir.
Okay,
So,
thank you very much.
Thank you very much, sir, for quite engaging and scholarly presentation of US. I would like to announce one thing. Kindly note that participants, the certificates would be granted to the participants recording their responses by filling up the feedback forms only. So the link will be shared in the Telegram group. So after these scholarly deliberations, let's move towards the closing session now. May I request Dr. Sarita Kumbhar ma'am from the Department of Physics to propose the vote of thanks. Over to you, Sarita ma'am. Sarita ma'am.
Good afternoon. I am Dr. Sarita Kumbhar is here to express vote of thanks for today's online seminar, Advanced Materials and Their Applications. There is overwhelming response from all parts of India to this seminar. On behalf of the college and physics department, I express my heartfelt thanks to keynote speaker, Professor Dr. A.U. Ubale, and chief guest, Professor Dr. P.S. Patil, for sparing their valuable time with us and guiding the audience. I am also thankful to our beloved principal, Dr. S.T. Saunke, for his constant encouragement and guidance for this webinar. I would like to thank the resource person of today's webinar, Professor Dr. S.D. Sartale, Dr. P.M. Shirge, and Dr. R.S. Devan from IIT Indore, who enlightened the participants with their presence and delivering very informative and knowledgeable speech. I would like to express my gratitude towards the convener of the webinar, Dr. V.V. Kiledar sir, HOD of Physics, and IQAC coordinator, Dr. S.M. Sathe sir, for shouldering the responsibility of the webinar. I would like to thank the organizing team, teachers, and staff members, without whom this webinar would not have been possible. Thank you very much. I am also thankful to Mr. Aniket Jadhav and their team for providing very nice technical support. I am also thankful to all the participants participating from various corners of India, without whom this webinar will not be successful. Thanks to all those who helped us directly or indirectly to make this webinar a grand success. Once again, thanks to all of you. Stay home, stay stay safe and stay digital.
Thank you, ma'am. With this overwhelming response from various regions, I am sure the webinar ensured the success of our event. We look forward to have the same enthusiastic and active response from our upcoming events too. Thank you very much.
Thank you, Devan sir.
Yeah, thank you very much.
Thank you, sir. Thank you. Thank you. A nice lecture, sir.
Yeah,
okay.
Thank you very much.
Okay. Okay, sir.
Okay, thank you.
You may switch off the screen, sir, your screen. Okay?
Okay, I will go. I have stopped sharing.
Okay.
Yeah.
Thank you, sir. Thank you. झालं सर त्यांचं हे करायचं का स्क्रीन सरांचं कसं आता कोण नाही ना एंड मीटिंग ना